Айрат Ахметович, здравствуйте.
Доброе утро.
Вас хорошо видно и слышно.
Вчера были проблемы с интернетом. Надеюсь, не будет сегодня. Проверил, вроде все нормально.
Тоже будем надеяться.
Народу пока немного.
Ну, это сейчас...
Айрат Ахметович, доброе утро.
Доброе утро.
Коллеги, доброе утро всем.
Доброе утро.
Да, вот сегодня с явкой что-то у нас не очень. Ну, может быть, подождем минуты 3-4, потому что сейчас без 3 минут 10. Это народ вчера заходил прямо ровно во время. Вот я следил за максимум посещениями. Порядка 60 человек у нас вчера зашло. Уникальных вот посетителей, но это достаточно неплохо. В основном это когда проснулась Европа.
По-моему, даже 61-62.
Ну, около 60 было, да, человек. Это, причем со всего мира практически были. Вот Азия, Япония, да, там Россия, само собой, и по европейскому континенту Италия, Испания, Германия, то есть, ну, неплохо, охват был очень хороший.
Александр Моисеевич, а скажите что-нибудь, пожалуйста.
Да, раз.
Просто от кого-то идет фон, кто-то в колонках сам себе в микрофон говорит, поэтому народ глохнет. То есть, поэтому...
Раз.
Вроде у вас нормально.
Да.
Вот, по-моему, это идет где-то от вас. Вы через колонки слушаете?
Нет. Хорошо.
Дмитрий, а у меня как, нормально идет? Без фона?
Нет, у вас это нормально, потому что у вас ничего не трогалось.
Хорошо, да. Собственно, здесь вот я смотрю в чате, англоязычных представителей нет пока.
Ну, на старте Кавасаки...
Попробую. Сейчас лучше?
Да.
У меня, может быть, бухгалтера колонки были.
Все, тогда ладно.
Хорошо.
Спасибо.
Все-таки у нас такой марафон получается. Вчера 7 с лишним часов, как смена у Столивара возле компьютера. Да? Позавчера 5,5 часов. То есть уже такой масштаб мероприятия состоявшийся. Ну, достаточно серьезный такой вес у события был.
Нет, ну серьезные ученые, действительно, много хорошего качества.
И вот Дмитрию удалось удержать вот эту бифуркацию, когда с расписанием пошел разлад, все-таки смог он вмонтировать
молодец
участников, и все все-таки состоялось без каких-то серьезных срывов. Но вот сегодня у нас коллеги из Азии, да, в первой части вот секционных докладов, но я надеюсь, что они проснутся к тому времени, что
Ну, они уже 5 часов плюс.
подойдут.
Так, трансляция уже первых 2 дней на Ютубе, то есть доступна, а 3-й день вот сегодня записываю.
Надо вот, у нас есть в УИП, может быть, там или еще где-то, чтобы поработать на предмет компоновки вот этой трансляции. ну, без, так скажем, посторонних там, включений. Там были некоторые моменты, которые нельзя допускать для размещения в общественном пользовании, мягко говоря.
Но это по, ну, скажем так, по трудозатратам это очень долго. То есть если ее монтировать и нарезать, ну, это как бы надо, скажете, заморочимся.
Нет, но если мы хотим, чтобы доступ к сайту и к содержанию конференции получило все мировое научное сообщество, то там надо ее, конечно, причесать немножко. Ну, давайте мы найдем, наверное, возможность так сделать. Потом, после окончания уже конференции, ресурсы найдем, да, Александр Моисеевич? Все-таки это лицо конференции, мы должны разместить все доклады.
Найдем.
Да. Поэтому сейчас пока пусть в таком виде, как только конференция закончится, сделаем этот видеоряд и еще раз разошлем всем участникам информацию о том, что в доступе вся конференция записана. Хорошо?
Хорошо.
Единственное, что были забанены куски из видео Тандона из-за музыки. То есть это уже точно. То есть там прям прерывалась трансляция на это время. Ну так работают алгоритмы YouTube. То есть они по авторским правам за музыку его вырезали. Но
у нас все равно где-то запись есть у нас или совсем нет?
Мы ведем локальную запись, но там надо смотреть. То есть мы вроде перестраховались 4 раза, а кто же знал, что авторские права так строго соблюдаются?
Ну, это вопрос, я думаю, решаемый. То есть у нас вот специфика в том, что мы же не собирали заранее материалы, да, для публикации. Вот, собственно, сама конференция, вот, если она останется в виде видеоряда, то это будет, собственно, содержание, да, этого всего.
Ну вот, кстати, мне Оля Величко сейчас пишет, что у нас же Тандон был пререкодер от презентации. Соответственно, мы ее просто вмонтируем цельным.
Да. Ну и
уберем музыку, да. А то люди из Индии любят вставлять музыку, даже научные действия.
Так, ну что, 2 минуты ждем и начинаем. Давайте.
Да.
Из первой части секции у нас 1, 2, 3, 4, 5.
А кто изместится? Кто изместится? Белов должен быть вроде. Я с ним вчера говорил.
Точно, потому что он по почте ничего не подтвердил.
Он вчера заходил несколько раз, так что...
Да. Да, Белов будет, скорее всего, точно. А вот... ну, то есть, там Дон, они вместе работают, они в одной команде.
Китай, наверное, зайдет в процессе. У нас еще вроде как 1,5 часа есть. А потом Евгений Арышенский из Самарского университета не отвечал. Ну вот из второй секции там, конечно, чуть ли не через одного, но есть чем занять.
Ну, будем ждать доклад Кабрера. Я думаю, что там все подтянется.
Ну, может быть, обсудить все-таки вот еще тоже, может быть, даже и где-то в середине можно обсудить предварительно. Все-таки 2 раза, вот давайте, 3 в месяц, как, или 3 раза в год, раз через 2 года или через 3 года проводить, не проводить ли, то есть мнение выслушать, в том числе иностранных участников.
Ну, более логично, наверное, 3.
Ну, наверное.
Так,
потому что за 2 года опять повторы начнутся. Ну, по крайней мере, вот то,
что... Раз в 3 года,
да.
Такой хороший.
Так, ну что, коллеги, начинаем?
Начинаем.
Да.
Dear colleagues, so the 3rd day is starting, and today we traditionally open this day by plenary session. The first report goes from Professor Nazarov from Institute for Metal Superplasticity Problems, Russia. Professor Nazarov, you're welcome.
Thank you, Mr. Chairman. Now I am sharing my screen.
Yes, we can see.
Do you see my screen?
Yes, yes,
My
everything is
presentation?
okay.
Hello, everybody. First of all, I would like to thank the organizers of this conference for inviting me to deliver a plenary talk at this conference. Alexander ZHILYAEV was my friend and a colleague at the Institute for Metal Superplasticity Problems. I knew him for more than 40 years. And in this presentation, I would like to tell you a few words about our studies at the university, a beginning of our work at IMSP, and then about our joint studies on the ultrasonic treatment of materials, on the problem which he was also interested very much. So something happens, I can't go ahead with my presentation. I remember exactly the day when I met Alexander for the first time. It was 26th July of 1976 when we both came to enter Bashkiria State University, and he was my dormitory roommate, group mate, and later the colleague at IMSP of Russian Academy of Sciences. I have not many photos with Alex ZHILYAEV, but you see what a couple of photos here with my roommates, Alex ZHILYAEV here, and the third, our friend Ramil Musalimov. He also was our room and group mate, and also he worked at IMSP. To be complete with our group mates working at the Institute for Metal Superplasticity Problems, I would like to mention also one more person, Valery Danilenko, who gave his presentation yesterday. He also was our group mate, and now he works at IMSP. And here, on a photo taken by me, you see Alex ZHILYAEV with Valery Danilenko in Ulan-Ude during Baikal Materials Forum. From 1981 till 1985, after graduation from the university, Alex stayed at Bashkiria State University at the Computing Center. I worked at Bashkiria branch of the USSR Academy of Science, and then both of us came to Ufa Petroleum Institute. After a short working there, we both came in 1986 to IMSP of Russian Academy of Science. And here you see, we worked at the Laboratory of Physics of Superplasticity, headed by Professor Ruslan Valiyev. And here one of photos taken around 1990, Alex and me and our colleagues taking tea during tea party in the laboratory. After defending his PhD thesis in 1995, Alexander obtained a postdoc position at McGill University in Montreal, Canada, and since then he worked at many research centers abroad. And his works during these periods of his life, participants of this conference know very well, mostly in the field of severe plastic deformation, non-structured materials. He worked very hard and became a world-known material scientist, author and co-author of many highly cited papers and books. Professor Langdon already showed some of his most important publications. This one is his review in progress in material science, and also he authored and co-authored several books, among them Bulk Nanostructured Materials, which was published in Wiley, and also on superplasticity and grain boundaries in ultrafine grain materials, published in Russian and later in English by him and his co-author Alexander Pshenishnyuk, our colleague from IMSP. And now let me come to the scientific issues of my presentation. In 2016, Alexander as informal co-principal investigator and I as a principal investigator, we won a grant from the Russian Science Foundation for the project, which was called Study of the Processes of Ultrasonic Treatment and Welding of Ultrafine Grained Metals and Alloys for Enhancement of Mechanical Properties of Materials and Application in Additive Technologies. By the present moment, the project was accomplished successfully, and Alexander contributed it with several fruitful ideas and provided high-quality publications. First of all, I would like to tell a few words about the mechanisms by which ultrasonic waves can influence the properties, the structure and properties of materials. Any ultrasonic wave induces in material displacements and accordingly also stresses, strains and stresses. So if we consider a dislocation on its slip plane, of course, this dislocation will experience oscillating shear strain from the ultrasonic wave, and this stress will produce a force on the dislocation, and the dislocation will make an oscillatory movement according to this equation. And then, according to this, there may be many different effects in the crystal, which are accomplished by dislocation movement. And I collected here several examples of the effects of ultrasonic treatment on the dislocation structure of materials. First, if we apply ultrasonic wave during the quasi-stationary deformation of material, in this case, the dislocations will be helped to overcome barriers which they experience during the plastic deformation, and due to this, the flow stress will abruptly decrease. Or if we have a deformation with constant stress, in this case, the strain rate will increase due to the effect of ultrasound. This effect is called acoustoplastic effect. Second, if there is a group of dislocations with non-compensated Burgers vector, like dislocation tripole shown here, in this case, despite the essentially symmetric change of the shear stresses acting on the dislocations, we will have a drift movement of this dislocation group in one direction. And of course, this effect will cause some structural transformations in the deformed materials. And the third effect is the refinement of loose dislocation walls, or we call it ultrasonic stimulation of polygonization. If due to the cold deformation, there is a loose dislocation wall, action of the ultrasonic wave will result in the transformation of these dislocation walls to fine plane dislocation wall. And this wall, of course, will have no long-range stress fields, and correspondingly, we will have some effect of polygonization. And finally, if the amplitude of the ultrasonic wave is high enough, this will result in the generation of dislocations by Frank-Reed sources, and there will be massive generation of dislocations during the ultrasonic treatment, and this will result in ultrasonic hardening of material. So we see that ultrasonic treatment is some kind of very versatile method of treatment of materials. And of course, it was very interesting to apply this method for the case of ultra-fine grained materials processed by severe plastic deformation. As already Professor ZHILYAEV told in his plenary talk during the first day of our conference, bulk ultra-fine grained materials which are processed by severe plastic deformation, for example, by high pressure torsion, they have a non-equilibrium structure. And the non-equilibrium character of grain boundaries in these materials are indicated, for example, by the transmission electron microscopic images of these materials. Here you see as prepared UFG aluminum alloy, and this one is after mild annealing of this material. And you see that here there is some diffuse contrast from the grain boundaries, indicating on the existence of high internal stresses. And here we have banded contrast of the grain boundaries, and this is an indication of well annealed equilibrium grain boundaries. And here you see a schematic representation of the non-equilibrium or metastable state of SPD processed UFG materials. Here, this is symbolically, this is a configuration with the lowest potential energy of the material in the configuration space, consisting of all the coordinates of all the particles, and the high energy metastable state after the severe plastic deformation. Of course, it corresponds to some state here, and in order to relax energies, we should overcome some barriers. And it's very tempting to come to this point from here by some kind of treatment. Non-equilibrium character of grain boundaries in UFG materials greatly affect the properties of materials, and there are some disadvantageous properties. For example, the ductility of these materials is much less than that of coarse-grained materials. And also here you see the dependence of the temperature of recrystallization of kappa on the energy, on latent energy of the material. And you see that when energy is low, the recrystallization temperature is more than 800 kelvins. And if we impart much energy by deformations, for example, by torsion straining, and you see the temperature of recrystallization will drastically decrease. And of course, this results in very low thermostability of microstructure of these materials. There is a method of structure relaxation in these materials. It is very known. It is mild annealing. Annealing helps to overcome some barriers and relax the energy. And by thermal treatment, for example, it's possible to increase the ductility of ultra-fine grained materials processed by ECAP method. But you see that the achieved strength is lost in this case, is greatly lost. So annealing will result in the loss of achieved strength of UFG materials. Another method is shaking. Here you see a pile of peas on a plate, and if we shake this plate, of course, we will see that the peas are distributed on the plate, decreasing the potential energy of peace. And this is the explanation of the effect of ultrasonic treatment on the structure of materials. It can relax similarly the energy of material structure and energy of the materials similarly to annealing, and we hope that this will not result in a decrease on the strength of UFG materials. There are several techniques of ultrasonic treatment of the bulk of materials, and the equipment which we are using is shown here. There is an ultrasonic transducer, ultrasonic transformator here, which increases the amplitude of vibrations, and this is the main instrument which is designed to clamp inside a disc-shaped material after HPT treatment, and clamping a material disc here inside it, we can subject the material to ultrasonic treatment, and then we measure the amplitude of displacements at the end of the instrument by capacity sensor, and the amplitude in microns is indicated here by the vibrometer. And the second method is instead of a steel instrument with clamped disc, we can irradiate directly half-wave sample, which can be obtained, for example, by equal channel angular pressing. And these samples are shown schematically here. This is a bar with the length equal to half-wave of the ultrasound, and this is the disc-shaped sample inside the steel instrument, and the instrument also has the length equal to the half wave of ultrasound. And the meaning of ultrasonic treatment is to induce standing wave in these materials. And when we achieve a standing wave in the resonance regime, in this case, we will obtain the highest normal stress, oscillating stress here in the middle, and zero stress here. On contrary, the displacement will be maximum at the ends of the cylinders. And the amplitude of displacement and amplitude of stresses are related by this relationship. E is the Young modulus of the waveguide for the case of material, for example, nickel, or for the case of instrument, it is the Young modulus of steel, and lambda is the wavelength. So using this method, we can subject to ultrasonic treatment different materials. And one of the most interesting results was obtained in 2014 in this publication. We irradiated a bar of nickel, UFG nickel, which was obtained by ECAP, and we irradiated it by ultrasound with the maximum of 100 megapascal normal stresses in the middle and zero stresses at the ends, and then cut this cylinder into 42 discs, and from each of them we cut 2 samples for tensile testing. And doing this, we were able to investigate the dependence of the effect of ultrasonic treatment on the strength and ductility of material. And here we have the corresponding graphs of ultimate strength, dependence of the ultimate strength on the amplitude of stresses of ultrasonic wave, and this one is the elongation to failure versus sigma 0. And you see that at the ends we have no effect because here we have 0 amplitude, and when the amplitude is 100, we see we are here, and at some intermediate amplitudes we have a significant increase in the ultimate tensile strength, and at the same time we also have an increase of the elongation to failure. So we see that at some amplitudes of the ultrasonic treatment, about 75 megapascal, we have a maximum effect of the simultaneous increase of elongation to failure and ultimate tensile strength. So this is some kind of paradox for the case of IUFG materials. Now I will show several results of our joint studies with Alex in the frame of the project. We we studied the effect of ultrasonic treatment with different amplitudes of stresses on the disc-shaped samples of non-structured nickel processed by high pressure torsion. And here you see electron microscopic 10 micrographs of the structures for the 6 values, for the 5 values of the stress amplitude. And from here, we see that at about 60 megapascals amplitude, we see some clearing of the grains from dislocations and relaxation of the grain boundaries to their equilibrium state. And again, we see that there is some optimal amplitude of the ultrasound, about 60 megapascals, when we achieve some relaxing effect on the structure. And we saw from our studies that the effect of ultrasound depends on the amplitude, and it is non-monotonic. First, it increases, the microhardness increases, grain size increases a little bit, and the excess energy of the grain boundaries also increases with the amplitude of the stresses. And at 60 megapascals of amplitude, we see that we have some relaxation effect on the structure and the properties of non-structured nickel. And then Alexander ZHILYAEV proposed an idea that we have to study the ultrasonic action on the structure of nickel, coarse-grained nickel. And he proposed an idea for the precision study. We took disc of nickel, coarse-grained nickel, in the well-annealed state, and by indenter we made some square, not 2 millimeters here, but it's my mistake, 1 millimeter square of with the 1 millimeter square. And we studied by EBSD the structure of this area after electropolishing. And then we subjected this disc to ultrasonic treatment in our instrument, as indicated schematically here. And then again polished the surface of the disc and studied the same area by EBSD in order to directly detect the structure changes which occur due to the ultrasonic treatment on this area. And we sonicated by this way several discs by the stresses of 20, 40, and 80 megapascals, and studied the microstructures by EBSD mapping. And here you see, for the case of 20 megapascals, the structures, and you see that the grain structure is the same. The grains retain their forms, their shapes in this area. No significant shapes of relative location of the grains, but there are different structure changes inside the grains. First of all, some twins or grain boundaries, small low angle grain boundaries which existed in the initial state, they disappeared after ultrasonic treatment. Some grain or small angle boundaries, like here in E and F, here, they migrated under the ultrasonic treatment. And there are also newly formed small angle grain boundaries here. For example, in this grain, they were no boundaries, and we have newly formed boundaries. So we directly see that there are great structural changes in the materials under the ultrasonic treatment. And here we have kernel average mesoorientation maps before and after ultrasonic treatment for the 20 megapascals amplitude. And you see that the green points, they indicate dislocations. Due to the geometrically necessary dislocations, we have change of the orientations of the pixels during EBSD, and this is an indication of the existence of geometrically necessary dislocations. And EBSD studies show that density of geometrically necessary dislocations increases with ultrasonic treatment. And this increase is even more higher when we increase the amplitude of ultrasonic treatment. After 40 megapascals and 80 megapascals, you see there are even greater structural changes. In the case here, you see very many new grain boundaries, small angle and large angle grain boundaries, and here you see the dislocations. And from this, we made several conclusions. First of all, let's consider the characteristics of the microstructure. Dislocation density, which is given by XRD measurements, you see that after ultrasonic treatment, approximately 1 order of magnitude increase of the total dislocation density occurs. Then EBSD also give the same, approximately the same increase, but we see that there is a steady increase of the density of geometrically necessary dislocations with the amplitude of ultrasound. And this is an indication that there is a formation of substructure during ultrasonic treatment. And this is also indicated very well by the fraction of low angle grain boundaries, which was very low in the initial state. After treatment with 20 and 40 megapascals, we have increase, and then it attains a maximum, again it decreases. And this means that at this stage, we have already the formation of large angle grain boundaries in the substructure formed by ultrasonic treatment. So we made several conclusions from this paper that this method allowed to demonstrate directly that under the action of ultrasound, an intensive generation of dislocation and evolution of substructure occurs. And with an increase of the amplitude of ultrasonic treatment, first we observe the formation of low angle grain boundaries, and then these grain boundaries, low angle boundaries, transform into high angle grain boundaries. By my opinion, this idea proposed by Alex ZHILYAEV was a beautiful idea, and shortly after the publication of these results in Material Science and Engineering A, we were contacted from Advances in Engineering, a Canadian establishment which positions themselves as the leading source of trustworthy and timely engineering research news, which ensures that the results of excellent scientific research are rapidly disseminated throughout the world in a fashion that conveys their significance for advancing scientific knowledge and developing innovative technologies for the benefit of mankind. And I consider that, and we published a short description of our results here. And so I consider that this result, which we obtained due to the beautiful idea of Alex ZHILYAEV, was worthy of publishing, was a kind of such news, and was worth of publishing in this site. I am grateful to Alex for inviting me as a lecturer to the Magnitogorsk Materials Week in the spring of 2019. Here you see a few photos with Alex Pygmy and Alex ZHILYAEV. I would like to finish my talk with this very symbolic photo also taken during our excursion to Magnitogorsk Metals Works. By my opinion, this symbolizes that Alexander was an outstanding researcher which was always interested in the secrets of metals, and he was a great friend. Thank you very much.
Thank you, Professor Nazarov, for your report. It was a really interesting historical overview by not only colleague but also friend. Colleagues, do you have any question? We have
I ask one question.
5 minutes.
Possible.
Yes, please.
What do you think? Thank you for interesting presentation. And what do you think about using incremental forging, maybe some effects, and maybe we can try to have reduction not only in near surface, but big reduction, maybe 3–5%. And maybe we can get better quality and better structure. What is your opinion about it?
You mean the reduction of the grain size or reduction of what?
It's reduction of the all volume of the piece
Yes. During forging, you mean the degree of deformation?
Yes, but incremental.
Yes, I understand. Yes, of course. There are many interesting publications now concerning the simultaneous application of ultrasound during the processes of plastic deformation, like incremental ECAP with the assisted by ultrasound. There are some publications about that, and also during forging, it's also possible. And even these effects were studied in the 1970s by the Belarusian group led by academician academician Kulubovich. Yes, they may be a huge effect on the process from ultrasound.
Thank you.
Colleagues, also questions. I have one maybe newbie question, but maybe you have such experience. What about generation of residual stresses by ultrasonic treatment?
Also possible, yes. Also, there are publications which show that using ultrasonic treatment also is possible to relieve the residual stresses after, for example, after rolling.
Mm-hmm. Okay. And also one question about some common steels, for example, low or medium carbon steels, where we have on micro level some kind of composite from something hard and something soft. Is it possible to apply this treatment for this kind of steel?
Possibly, yes. We didn't study steels yet, but we have some little experience. We are beginning some works on copper alloys with Professor Rapp, and we see that we already see that there is an effect on the precipitation of particles. So I think that ultrasonic treatment of steels also can change some, sometimes the composite structure.
Okay. Okay, thank you. Colleagues, do you have any questions? No. Thank you for your report. Next
Okay,
report.
thank
Next report goes from Professor Pesin. Professor Pesin, you're welcome. We see your presentation, but your microphone is switched off. В левом нижнем.
Is it okay?
Yes, yes, you're welcome.
Sorry. Wait, I'm sorry. Wait.
Можете F5 нажать просто.
Да.
Курсор в презентацию поставьте и
Я... Сейчас, одну секундочку, я заново сделаю. I'm sorry. Okay. Is it okay?
Yes, yes.
Yes. The theme of my presentation is ZHILYAEV Laboratory of Gradient Nanomaterials and New Technical Solution in Metrology. Today we'll speak about theme which you can see in content. At first, I decided to show you a short movie about Magnitogorsk and NMSTU in our university. I think it will be useful for people who.
Magnitogorsk is a major center for business, industry, culture, and tourism in the southern Urals. The city's centerpiece is the 15-meter rear front monument, which was unveiled in 1979 and forms a part of a triptych.
It's too loud.
In securing victory in World War II. The second part can be found on Mamayev Kurgan in Volgograd, and the third in Treptower Park in Berlin. Magnitogorsk is one of only 12 transcontinental cities in the world. The Ural River runs through the city, dividing it into two halves, one in Europe, one in Asia. In addition, the city is famous for its arena Metallurg, home to the ice hockey team of the same name, who are multiple-time champions in Russia and Europe, and the current holders of the Gagarin Cup. The mountain ski resorts in the area surrounding Magnitogorsk are famous throughout Russia and attract more than 200,000 extreme sports enthusiasts each year. Magnitogorsk has come to be known as the Steel Heart of Russia. This is because the city is home to the Magnitogorsk Iron and Steel Works, the country's largest ferrous metallurgy enterprise, as well as one of the world's leading steel-making companies. The city's main higher education institution is the Nosov Magnitogorsk State Technical University, NMSTU. one of Russia's most prestigious multidisciplinary technical universities. The university boasts a developed infrastructure, impressive facilities and equipment, and high-level intellectual resources. The university is home to over 20,000 students, 2,500 teachers and staff, 100 professors and doctors of science, and 700 associate professors and candidates of science. Teaching is carried out in the fields of metallurgy and mechanical engineering, energy production and automated systems, construction and architecture, economics and management, mining and transport, information technology, pedagogy and psychology, as well as in history and linguistics. Approximately 5,000 qualified specialists graduate from NMSTU each year. 3 institutes operate on the university site: the Center for Innovation and Technology, the Technology Park, and the Student Business Incubator. The university is equipped with several modern libraries, which give students access to more than 1 million publications in science and technology. The university today collaborates in the fields of education and science with more than 60 foreign universities, foundations, and organizations from 28 countries, including France, Germany, Italy, Poland, the Czech Republic, Japan, Turkey, South Africa, India, Bulgaria, Brazil, and China. NMSTU also has an active student life with 13 art societies, 24 sports departments, 6 student associations, and more than 50 major cultural events each year. NMSTU has set up a number of convenient and pleasant spaces for the leisure and cultural pursuits of the university students and staff, notably the University Gardens. NMSTU is the only university in the region to independently organize health resort therapy for its students and staff at the Youth Training and Wellness Center located outside the city. Great hopes and far-reaching plans lie ahead for this young and fast-growing university. Here in the very heart of the city of fire and metal, the doors of the Nosov Magnitogorsk State Technical University are always open to new colleagues and new ideas. NMSTU, your future begins here.
Our laboratory was created in 2018 within the framework of the mega grant under the degree of the government of the Russia Federation, number 220. The first head of the laboratory and the invited scientist was Dr. Alexander ZHILYAEV. Today, Dr. Grigory Raab is a new head of the ZHILYAEV Laboratory of Mechanics of Gradient Nanomaterials. Our laboratory is named after ZHILYAEV. Our laboratory has 5 departments: computer modeling department, department on physical modeling and mechanical testing, technological department, department of microstructural analysis and optical microscopy, and electronic microscopy. We have 4 academic schools. Of course, many people, the most people in our staff is from our university. We collaborate with MISIS and Ufa State Aviation Technical University and Institute of Ultra Plasticity from Ufa and Russian Academy of Science. In this slide, you could see the information about our staff. And one more movie about our laboratory, about equipment of our laboratory. Sorry.
Here we are at the technical office of our lab. Behind me, there is a unique asymmetric rolling mill 400. It is extremely powerful as it can roll steel sheets reaching a reduction rate of 75 to 80%. The maximum rolling force is 250 tons, and the maximum power is 200 kilowatts. This rolling mill enables to obtain gradient structure, meaning that one side of a steel sheet will have an ultrafine grain structure, whereas the other side will have a structure consisting of coarse grains. This makes that sheet ductile and strong at the same time. Besides, this rolling mill can simulate production of bimetallic bands or laminar materials. Here you see a Kuka robot with the maximum force of 160. It has 6 degrees of freedom. At our lab, it is used for incremental forming. Thus, we use our rolling mill to produce steel sheets, which we then deform with the help of this robotic arm. What you see here is a lab machine for simulating various modes of symmetric and asymmetric rolling, so one can better understand the effect of friction and rolling rates. It works with flat workpieces 2 to 5 millimeters thick, made of different materials such as titanium, copper, aluminium, and steel. And now I'm going to show you how it works. Here I have 2 specimens. One is before rolling and the other one is after rolling. The reduction rate is about 50%. To obtain a gradient structure in materials, we apply impact loads. The aim of our research is to understand the effect of the impact range, frequency, and force on the structure. For such testing, we use this servo pulsar. It is a hydraulic unit designed for cyclic tests. To show you how it works, we set it for a frequency 10 times lower than the normal frequency. The results of our research we're going to apply for the Kuka manipulator available at our lab, and the plan is to actually apply it for a real-life production line. In this room, we have 2 tensile test machines. They are used to test specimens after they have been processed in our lab. One machine is designed for 5 kilonewtons, the other one for 30 kilonewtons. This particular unit is designed for a force of 30 kilonewtons. It is equipped with a non-contact video extensometer, a high-accuracy device that measures displacements. The measurement accuracy is up to 6 microns. The unit can perform tension, compression tests, as well as 3-point bend test. This is a specimen after a 3-point bend test. Microstructure is the key parameter that determines the mechanical properties of steel products. For this, an optical microscopy section was established at our lab. It includes a specimen preparation unit, an optical inverter microscope for processing and identification of surface microstructure Tixamet, a stereom microscope, units for duraluminum studies. Here we also have a multi-purpose device for measuring hardness, that is Vickers, Brunel, and Rockwell hardness. The main aim is to analyze the hardness of separate structural elements and areas of gradient structures. We use a micro hardness tester and an ultra micro hardness tester. that enables to measure the hardness of ultrafine grain structures and nanostructured elements. It is often the case that the magnification of a regular optical microscope is just not enough when analyzing gradient materials, not to mention gradient nanomaterials. For such cases, a scanning electron microscope like this one comes extremely handy. It enables a wide range of magnification from the optical range to a magnification of 100,000 times and more. Besides, this microscope can produce deep focus images which enable to thoroughly study fracture surfaces in specimens after mechanical tests. This unit has two attachments. One is for X-ray microanalysis. It enables a local chemical analysis. It can also analyze bimetallic materials, which is what we're actually studying under this project. And the other attachment is designed for EBSD analysis for crystallographic or textural characterization. We can build distribution charts or grain misorientation charts, and so on. This physical modeling complex is used to understand the possibility of obtaining ultrafine grain structures as a result of hot and cold forming. Heat treatment is one of the main techniques for material processing, and this unit enables us to realize almost all heat treatment processes to obtain critical points and phase transformation points.
We really have unique complex of technological equipment of the laboratory. We have a real chain from the beginning of the metallurgy production. For example, from the vacuum induction melting furnace with continuous casting machine at the beginning of the chain, and at the end of it we have industrial laboratory asymmetrical rolling mill and robotic complex, which gave us possibility to use stamping and to get machine building production. We have a wide international collaboration and a good connections with leading Russian groups and centers. We have got regularly grants, Russian and some foreign grants, and every year we are organizing 3 conferences and seminars. And one of them is Magnitogorsk rolling practice. Our city is unofficially a capital of ferrous metals of Russia. And it's maybe the best place where young people, young students, postgraduate students and young scientists could meet with each other and connect and establish connections and continue to collaborate with each other. And this is a really good way, and I invite you this year, and in the finishing part of our conference, I think that we can tell you about the dates. And I want to tell you about Magnitogorsk Materials Week. The idea of this conference was from Dr. ZHILYAEV, and initially it was seminar for young people, for students, for maybe for not only young people. We invited several famous scientists who gave lectures for the whole week. Every of them 5 lectures, and now it's 5th Magnitogorsk Materials Week. We have 2 materials, Magnitogorsk Materials Week every year, in autumn and in spring. But today we have another format. Today we have conference in memory of Dr. ZHILYAEV. And I think that maybe if you support us, we can continue this conference maybe in one time in 3 years. And now I have two reports today, and if I can continue in next my time, I want to tell about the presentation, about relevance of the problem. For the last 80 years, there were no radical changes in metallurgy, in ferrous metallurgy. In another fields, we can see very rapid changes. For example, in 2018, we can see a launch of trains that can travel as fast as 1,200 kilometers per hour. In 2022, they promised that our aircrafts capable of flying from London to New York in 1 hour. In 2024, Musk promised that his rockets capable of flying from London to New York for a half of an hour. They could grow human arms and legs and so on. And should we expecting to see a major breakthrough in metallurgy soon? And may I ask you child questions? In ancient time, they would bomb trees and use the carbon from the trees for iron reduction, but it was not very efficient. So nowadays, they use coke instead of trees. What is a child question? Does the carbon really make the best deoxidizer? Of course not. But why we use carbon? Why don't we try to and add small amounts of something better than carbon to the melt? In a conventional PROF process, scrap metal account for 23%. Today, scrap metal prices exceed about $300. Why don't we use something else to substitute a portion of scrap metal in the process? Iron and steel makers produce a lot of slag. Why don't we capitalize on the fact that it comes in liquid state? Can we extract something from slag while it is still hot? Recent years, some numerous plate mill installations around the world, especially in China, some of the plate mills have a tight production schedule, and some of them are looking for more orders. Can we use plate mills to produce machine parts, for example? Today, the scrap metal markets offer a product with 95% of ferro. Why we don't have a product with less concentration of ferro? In the shipbuilding industry, we connect with the problem of heat cracks that occur when rods are welded to steel plates. Such plates get automatically ejected. can't we come up with a new plate profile which guarantee us from this problem? And there is a problem with adhesion between concrete and steel in reinforced concrete columns. And we can continue. And let me speak about some decisions which were getting off our laboratory. In PROF process, when compacted bundles of semi-finished product are used as solid charge before compacting gas permeable capsules and placed inside the bundles, which are filled with a special substance. And we can help save up to 20% of metal scrap. It's a very big sum only from one iron and steel works. It is proposed to use new catalysts for the production of cast iron. Before maybe last years, we can't do with the problem of the carbon, but now we can use in nanodose, for example, aluminium and so on. And we have decision how to do it. We can organize production of new profile from plate steel for ship and bridge building and for the production of reinforced concrete. And this profile guarantee from the problems in both variants. Iron and steel makers produce a lot of slag. We can capitalize on the fact that iron and steel makers produce a lot of slags in liquid state. After mixing them in a liquid hot state and adding additional components, we will be able to produce basalt. Traditionally, in the production of basalt, 90% of cost is accounted for heating and melting of stone. And using liquid hot mixes, we have got significant savings in production of basalt and in getting utilization. And we create new methods to produce large size bodies of revolution production on the plate mill. Nobody in the world produced the same. And you could see the first combined process. It's very short movie in industrial application. And another new combined process of plate rolling and stamping. And you could see that we can produce a bottom part of the very large aggregate. And I have maybe 2 or 3 minutes. And we have some decisions in creating a technology of asymmetric rolling and asymmetric cryo rolling and asymmetric accumulative rolling. And I will speak about it in my second report, maybe more. And I don't want to speak this now in about asymmetrical. And another interesting theme is to produce bimetals, and this is a very main for our opinion to produce contact surface, the shape of contact surface. And we have many patents in this field, and now we are working and try to find rational shape of the contact surface for good, so for better adhesion and so on. We have work in incremental rolling, drawing, and forging. We in contact with Professor Tandon and Professor Yu from India and China. Some decision. And we begin to use robotic incremental sheet forming. New equipment appeared only on March. Our rolling mill was began to work maybe on 5th of March, and now maybe about a month from the beginning of his work. And I think that we have some results, but I think that most of them will be further. And one more, the next our direction is concept of design of materials and structures, assemblies of interlocked topological elements. And we have some decision. We are working with Australian partners and with Israel partners. And I think that we have about maybe about 8 applications for patents. And I think that's some good ideas. We try to use this conception. It was born in maybe about 15 years ago, but I think that now it can get the second life. I know that some department of MISIS is working under this problem, but we try to use this problem in technique and methodology, in mining, in building industry, and so on. And thanks for attention, and I will continue in the next my presentation. Thank you.
Thank you for your report, Professor Petin. It's nice to see that laboratory becomes bridge between fundamental research and real industrial application. So, colleagues, do you have any question? So I have one question about your rolling mill from the beginning. How is it flexible for production of wide range of products, steel sheet products? What size limitations do you have? What materials limitations, and so on and so forth?
I think that we can use many materials. We try to organize rolling with titanium, with aluminum, several series, with steel, with copper, and so on. And we have got about maybe from 65 till 80% of reduction for one pass. Of course, it depends on the width. It depends on the the kind of the material. But I think that we try to have mill for automobile steels, not steels, for automobile sheets. For example, we have the mill 400, and you could see the width, and the minimum is about maybe 0.5 here, not less to my mind. For symmetrical rolling, in symmetrical rolling it could be less, because there is a problem, not problem, but this is a dangerous if the rolls with different speed can contact with each other. It's not good, because but I think that it's not good to have the distance less than 0.5 millimeters.
And is it possible to make equal speeds on both rolls immediately?
Sorry.
Can you provide equal speeds on both rolls?
Yes, of course. We have it possible to we have called symmetrical rolling, warm rolling, asymmetrical variants of rolling, cryo, and so on. Bonding.
And one more question, maybe do you have, or maybe do you plan to have some specific roles for example, rod production?
I think for this mill, no. I think it's not good idea to mix them. I think that we will have equipment for heating of the rolls to produce materials which is needed short diapason for in temperature, because it's dangerous for cracks and so on.
Okay, colleagues, do you have any questions?
No, I have one more presentation today, and I will speak about asymmetrical rolling maybe wider.
Okay. Colleagues, do you have any questions? We have a few minutes. No. Thank you. So thank you for your report. We should go to the section with reports, but I don't see Professor Wang from Australia in chat. Professor Wang, are you here? Unfortunately, no. So it means that we have some kind of coffee break. I think it's really important for our foreign guests because, for example, in Italy, it's early morning now. So we have 20 minutes. See you soon. Thank you. So we can continue. Professor Son, you're welcome. You can test your presentation. Hello.
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 We hear you.
Yes, I can hear you.
So we see your presentation. You're welcome.
Yes. Thank you very much. Ladies and gentlemen, my name is Song Lingying. I'm professor with student come from Central South University, China. It's my great honor to attend this meeting. My presentation title is Microstructure and Mechanical Properties of Accumulative Rebounding AA1050A5052 multi-layer composite sheet. The main content includes 4 parts: background, experiment, results and discussion, and conclusions. First, I want to introduce some background. With the continuous improvement of the requirements of modern production on the comprehensive performance of materials, in many fields, a single material has been difficult to meet the requirements of use. In the past 20 or 30 years, composites have been developed widely concerned by researchers. All kinds of composites and their preparation methods have been developed rapidly. One of the most important branches is laminated metal composites. A typical laminated metal composite was found to be the Achilles shard of 800 BC, consisting of 2 layers of bronze, 2 layers of tin, and 1 layer of gold. In addition, many ancient salts also use the principle of laminated metal composites, such as the corrugated salt of Middle Ages, the famous Damascus salt, Tang salt, Japanese samurai salt, and so on. Historically, laminated metal composites have been produced for 2 reasons. One is to improve the overall mechanical properties of the parts. The other is to reduce economic costs by overlaying the precious metal with cheaper metal materials. Modern research on laminated metal composites reported in literature began in the 1960s, when the United States took the lead in putting forward the production process of surface treatment called rebounding, annealing strengthening, which started the research boom of laminated metal composites. However, for a long time, the high manufacturing cost has limited the industrial application of laminated metal composites. The practical engineering application of laminated metal composites began in the former Soviet Union, when the Moscow Institute of Steel and Alloys proposed a unique radial shear spiral rolling technique for the formation of steel and steel laminated metal composites, which is widely used in large pipelines and large pressure vessels. In 1999, SIDO put forward a more economic and effective method, a cumulative rebounding process, to manufacture laminated metal composites on the basis of cold rebounding, so that laminated metal composites really went out of the laboratory and began to be applied in a wide range. Laminated metal composites have been widely used in power, chemical, metallurgy, automotive, aerospace, and so many other fields. In the 21st century, the study of laminated metal composites, preparation technologies, material system more prosperous. The following are 3 commonly used preparation methods, including explosive compound method, depositional compound method, and the rolling compound method. Rolling technology is through the pressure of the roll to make different metal plastic deformation and welding together, which is the most widely used to produce laminated metal composites. In the following, I will introduce a few examples about the preparation of laminated metal composites using accumulative rebounding. Sedgenier found that the resistance of aluminum and titanium composites fabricated by accumulative rebounding significantly improved with the increase of the number of cycles. Madivin reported that the curve layer began to lag in the false path when ultimate tensile strength reached its maximum value. John discussed the effect of annealing after rolling on the thickness of diffusion layer of titanium and nickel composite sheet, and found that heating could not only increase the thickness of diffusion layer, but also change the diffusion mode. Moore studied the effect of annealing on the microstructure and mechanical properties of accumulative rebounding processed composite sheet. He compared the mechanical properties of the rolled and aged composite sheets and concluded that the composite sheet obtained the best mechanical properties under the natural aging condition. Although the accumulative rebounding process can be easily performed with conventional rolling equipment, less restrictions on the material, and has the ability of mass production sheet, and can refine the grain size. But with the increase of strain, the rate of grain refinement becomes more and more inefficient, while chloride rolling by decreasing deformation temperature can reduce the grain size of the limit. By the combination of accumulative rebounding and chloride rolling processes, the laminated metal composites with excellent mechanical properties can be produced. The experimental method of this study is divided into 4 parts. The first is to recrystallization annealing of starting materials. The second is using accumulative rebounding to prepare 2 groups of the multi-layer composite sheets. Rolling passes are 3 and 5 respectively. Then 2 passes of chloride rolling is carried out for the 3 passes of accumulative rebounding process a multi-layer composite sheet. The reduction of per pass is 50%. Finally, the mechanical properties and the microstructure of the composite sheet are tested and characterized. The following is the analysis and discussion of the results. The figure shows the tensile properties of the composite sheet in different rolling states. In the first 3 accumulative rebounding passes, the ultimate tensile strength increases with the increase of the number of passes. And by comparing the tensile properties of the 2 rolling schemes, the ultimate tensile strength is significantly improved after chloride rolling, while it begins to decrease from the false accumulative rebounding pass, see figure B. It can be concerned that the fracture of the hard layer is a dominant factor for the decrease of ultimate tensile strength. There is almost no difference in the variation trend of elongation. The microstructure characterization will be introduced from 3 aspects: element diffusion, rolled sample layer structure, and tensile fracture. The results of diffusion detection of magnesium element indicates that there is diffusion of magnesium element between the 2 constituent layers during the rolling process. And in the 5 accumulative rebounding process, the hard layer begins to appear obvious necking from the false pass, which is showing that plastic instability has occurred at this time. In order to further analyze the element diffusion at the interface of the composite sheet, the first pass of chloride rolling profile sample is performed area skin and line skin. According to the second phase particles and the content of magnesium element, 2 constituent layers can be clearly distinguished. Figure C shows a certain different depths of magnesium element at the interface of the composite. It can be seen from the layer structure that the thickness of the layer decreases with the increase of the applied strain. No cracks and micro walls occur at the interface, and the 2 layers are well bonded. In the first 3 accumulative rebounding passes, the two constituent layers can maintain uniform co-deformation, and the hard layer remains straight and continuous. However, the thickness of the hard layer changes irregularly along the length direction after the false pass. In other words, the hard layer occurs necking at various locations. After the fifth pass, the hard layer begins to fracture along the necking and forms lenticular fragments. In contrast, cry rolling can delay the onset of necking and fracture. The tensile fracture analysis shows that the interface bonding is weak at the initial stage of accumulative rebounding, and obvious delamination can be observed after tensile fracture. In these weak bonding positions, the initial and propagation of microcracks will occur, which will lead to the fracture of the sample. However, with the increase of the applied strain, the bonding quality of the interface is continuously improved, which can be confirmed by the increase of ultimate tensile strength. Many dimples can be observed in the tensile fracture, indicating that all specimens are ductile fracture. And by raising the number of accumulative rebounding passes, the dimples are decreasing in size, depth, and number, which results in a decrease in ductility. In addition, the interface bonding quality is greatly improved under cry rolling, which is one of the reasons for the improvement of ultimate tensile strength in cry rolling compared with 5 accumulative rebounding passes. Finally, the conclusions of this study are drawn. First, the ultimate tensile strength of the multi-layer composite sheet prepared by accumulative rebounding increases first and then decreases. The decline of ultimate tensile strength from the false pass can be attributed to the plastic instability of the hard layer. Second, accumulative rebounding processed the multi-layer composite sheet, subsequently subjected to cry rolling, has higher strength compared to 5 accumulative rebounding passes. Due to cry rolling accumulates higher dislocation density by inhibiting dynamic recovery and delays the onset of necking and fracture, the ultimate tensile strength can continuously increase. Third, investigation of the tensile fracture morphologies indicates that the fracture mechanism is ductile fracture. Moreover, cry rolling can improve the bonding quality of the 2 constituent layers, making no delamination phenomenon across fracture. Okay, that's all. Thank you.
Thank you for your report. Dear audience, do you have any question? Professor Pesin.
One second. Yes, in cry rolling process, of course, you have limitation in temperature, because if you have a very big reduction in one pass, the sample the temperature of sample begins to increase, and it's not good for cry rolling. But what is the limit of reduction? Have you, for example, 1%, maybe more? How, in one pass, what is the limitation of the reduction in cry rolling process, for your opinion?
We have done another set of tests rolling at 173 K, but the test results have not been sought out yet. It may have different mechanical properties in other cryogenic environments. We will still working on it, and I will continue to explore this research direction.
Okay, because I ask you, because it's a problem, one problem, because you want to have all time the temperature as less as better. And but when you have rolling, there is a deformation, and after during the deformation, the temperature begin to increase, and of course you have to increase productivity. You have to have as more as possible reduction in one pass, but for the goal to decrease temperature, you have to decrease reduction, and it should be some optimal reduction in one pass. Maybe.
Sorry. The deformation in cryogenic environment is 50%. So
it's summary deformation. It's
summer deformation.
One pass. What is the reduction?
Reductions. Summer deformation is 75% in cryogenic rolling.
But for one pass. Okay, thank you.
Okay.
So, colleagues, do you have any question?
Sorry.
We have two questions in chat. Professor Son, could you check? Have you measured the thickness of the transition diffusion layer?
Sorry, my network is poor. It's weak. My network
okay, but could you check questions in chat?
Questions in chat.
There are questions from Biryukova, Olesya. Two questions in chat.
Two questions. The diffusion of magnesium element. This magnesium element diffusion depths. Before rolling, I have before accumulative rebounding, I have surface treatment like brushing. The diffusion depth is about 5.79 and 5.85. Before rolling, I have winding and cleaning, like the accumulative rebounding pressures.
And okay, thank you. So, and more questions, colleagues? No. Thank you for your report.
Thank you. Thank you.
Thank you for your attention. And the next report goes from Arseny Russia. Arseniy, are you here?
Yes, I am here.
You're welcome. You can share your screen.
Arseniy is a member of the laboratory of ZHILYAEV, ZHILYAEV Laboratory of Mechanics of Gradient Nanomaterials.
You see my presentation?
Yes, everything is okay.
Okay. Good afternoon, dear colleagues. I am pleased to welcome you and would like to present a report on methods for obtaining gradient structure and properties in bulk materials with possible practical application of gradient materials in industry. At present, there are many ways to obtaining nanostructure materials, and the most popular of them are HPT, ZHILYAEV conform, which allow to obtain materials with nanograin from coarse grain materials by means of shearing schemes. Such materials have high strength but low ductility, which imposes certain restrictions of their application in industry. Development of methods of obtaining gradient bulk materials allow creating new promising materials and expand the range of practical application of the obtained materials. In the present work was set a task to study the influence different deformation schemes of the change in the deformation intensity and corresponding transformation of the structure that occurs in materials under this treatment, and also to determine the relationship between this change and mechanical characteristic. One of the investigated methods for obtaining gradient structure is the method of free torsion of billet in the form of a rod. The method is simple. The ends of the billet are fixed by two grips, and one grip is in a stationary state. The second is rotated relative on the longitudinal axis of the billet, due to which the shear deformation occurs in the volume of the billet. Technical features: single cycle treatment, cold and warm deformation, advantage use of standard equipment, possibility of realization of high rate of pressing, low cost of ancillary equipment, accumulated strain up to 6. Size and shape of produced billet, longitudinal workpiece of constant section, variable size of samples. Limitations: limited range of samples received. The results of virtual experiments showed that a gradient of properties is formed in the deformed billet. Shear strain intensity during the free torsion has a gradient character and depends on the number of turns. So then the maximum number of turns is reached, and in the peripheral layers up to E equal to H, while maintaining the integrity of billet. Computer simulation results show gradient distribution of accumulated strain intensity with E equal to 5.9 and E equal to 2.7. Free torsion of cylindrical workpiece in the longitudinal and cross section leads to formation a gradient type microstructure towards the peripheral regions in the workpiece with grain size ranging from 50 micrometer in the center to 1 on the periphery. Studies of the mechanical properties of the samples using Vickers microhardness measurements reflect to the distribution of accumulated strain and are also gradient in nature with maximum values up to 200 HV in the periphery and 125 HV in the central region. Other method for making gradient structure, the method of drawing with shift. The essence of the method consists in pulling a billet through a special drawing which consists of two parts. One part is forced to rotate about the longitudinal axis, which a channel is made asymmetrically, resulting in a shear deformation of the billet while driving. Technical features available multiprocessing, cold and warm deformation, size and shape of billets, bulk, bullet, round, cross-section, advantage, using standard equipment, continuous process, low cost of additional equipment, possibility used in the process of mass production, non-monotonic character of deformation, future of the method, application of shear deformation during drawing. For the analysis of this proposed method was used computer simulation with the following boundary conditions. According to the simulation, results of strain intensity were obtained in the cross-section of the workpiece. As can be seen, a gradient of properties across the section after the drawing method with a shift was used. This is clearly shown by comparison charts with traditional drawing. To realize this method, a special unit was made to allow us to set the rotation of the component drawing frame. It can be mounted on a chain drawing machine and experiment with it. Three options can be offered for this method. One, shear drawing pass pre-deformation followed by conventional drawing and as a finishing operation after conventional drawing. Microstructure analysis of samples from different materials also shows the effect of using this method. So a layer of 25 microns in depth with hardness up to 350 HV is formed in titanium. On copper, the depth on the layer is graded to 160 microns and also to them an increase in hardness up to 350 HV. In steels, the depth on the layer is 140 microns and the increase on hardness is 3 times up to 700 HV. Analysis of the method revealed limitations. This is deformation heating and the need to select speed parameters during deformation. However, the proposed methods allows the formation of a gradient structure which is PD on the surface and with a large grain on the core of the sample. The possible application of the resulting wire rope, special wire contact wires. Another method to severe plastic deformation allows to obtain materials with a gradient structure, a rolling method with twisting of the rod. The scheme of the method is presented on a slide. The device includes 2 rolling rolls and a twisting unit. Technical features: single cycle treatment, combined processed cold and warm deformation. Advantage: use a standard equipment, continuous of the process, possibility of the realization of high rates of processing, low cost of ancillary equipment. Size and shape of produced billet: longitudinal workpiece of constant section, variable diametric size. Limitations: limited range of sample received. For the virtual analysis of this method of use, the following boundary condition. According to the results of the simulations, graphs and patterns of the distribution in the strain intensity of the bar cross-section were obtained, from which it is clear that a gradient of properties is observed in the cross-section for different twisting angles. The results of computer modeling show that the twisting angles of the workpiece affect the accumulation of strain intensity in the surface layer of the workpiece, and the difference with the central region is 2.5 times. The result of a physical experiment also showed that a rod was formed in the form of reinforcement, and an increase in micro-hardness over the cross-section was observed. Thus, the stretch characteristic of the sample increased by 30% compared to the initial state. Possible areas of application: producing rods with high stretch hardness surface for reinforcement, twisted reinforcement of constant cross-section for concrete products with increased stretch. Explicit result: increase the wear resistance of service life. Another method for producing long bars with a gradient of properties is called rotary active alternating bending. A schematic diagram of the methods is presented on a slide. The device consists of rollers through which the workpiece is pulled and bent. Also presented various options for using this method. The deforming unit for realize this method can also be quickly mounted on a chain drawing machine. For the virtual analysis of the methods of used following boundaries condition. Mathematical modeling of the methods was implemented in the deform, and the results of the virtual experiments revealed the formation of a gradient of properties in this sample. As can be seen from the present graphs, the intensity of the deformation in cross-section of the sample varies considerably from surface to center. And strain effective increase up to 3 times after 4-pass bending. Microstructure analysis after 4-pass bending showed the formation of a structure gradient over the simple cross-section, sample cross-section. The study of the sample after the physical experiment, it showed that there is a gradient of properties over the cross-section of the sample, which an increase in micro-hardness on diameter. And on present advantage of rotary active alternating bending method: continuous process, constant cross-sectional shape, low metal losses, increase resistance of bars to surface wear, increase resistance of bars to longitudinal bending, possibility of use in the process of mass production. Possible application: contact wires for high-speed railways, which are used in intensive modes and required surface strength and ductility in the core of the wire. The studies showed that the SPD methods can provide the formation of a gradient type of structure in lengthy workpiece with an increased level of strength in the peripheral layers of the cross-section. Future of the studied methods: gradient properties over the cross-section of samples, intensification of hardening, and the formation of high hardness of the surface layers, reducing the unit load on the tool, hardening on the peripheral surface on deformable samples without restriction, and the formation of internal defects. Thank you for attention.
Thank you, Arseny, for your report. Colleagues, do you have questions? Piotr, we don't hear you.
May I ask, please?
Now it's okay?
Yes, yes.
Arseny, thank you for a nice presentation. You show like a lot of mechanical modeling in your presentation. In what framework you did your modeling? It was finite element method.
Yes, deformate the finite element method, and
how many elements did you use on average?
Different process used different number of fine elements. It's 150,000.
I see. Oh. So this was the largest number of elements, or it's the average?
Oh, this slide is show the conditions and assumptions simulation.
And the mechanical modeling give you the stresses during the processes that you obtain. So it doesn't give you the grain structure.
Structure. Modeling structure.
Yes, yes.
Ну, я имею в виду, что структуру механическое моделирование не давало, да?
No.
For structure simulation, I think in this case, it would be great to apply multi-scale simulation with microstructure representation by any software what you want. I have one question about slide number 7. Yes. In this process, we have a rather long contact zone between two tools and one billet. What lubricant do you use for such process?
No, this process used classical lubricant and based on graphite.
Okay. And is it enough for such conditions of treatment of friction?
Yes. Okay.
Okay. And also one not question, but discussion. It will be great if you make cutting of your real samples not in cross section, but in regarding drawing direction, because it is really interesting how this process change texture formation and grain orientation.
About this, yes?
Yes. But this is picture in longitudinal direction, yes?
Да, продольно.
Продольно, окей.
No, for bending this slide is present longitudinal properties of billets. These slides also show the longitudinal and cross section. Так, ну в основном, да, наверное, поперечное течение.
Okay.
Так,
And-
only bending showed the longitudinal.
Okay, thank you. More questions,
Can
colleagues?
I ask? It's not a question, it's something like to think in loud. About drawing with share. If I'm not mistaken, just a second. In Poland once I saw a drawing with some kind of share, I mean, but not, but they didn't
Yes, yes.
rotate the sample. They use different steps. I mean, one direction, and then there is a step.
Yes. So this is a cumulative angular drawing
Yes.
from Professor Mushka.
Yeah, and I'm wondering what could be advantages or disadvantages or difference of these methods. I mean, which of them could be better? But it's just general questions to think about.
In general, this process from our Polish friends uses rather difficult scheme of rotation with rotation of die, rotation of between dies, and so on and so forth. And I'm not quite sure about the results because it is too difficult for even for medium carbon steel.
They use it on titanium. I mean, they showed the results on titanium in Poland. So
Maybe due to unpleasant conditions for regular steels. Who knows? So, Professor Pesin, do you have a question?
I have a question. Arseny, what is the problems you can you see in using your process? It's interesting. Thank you for presentation. It's real interesting. But what is the problem? What is the limitation, maybe constraints in using them?
One of the problem is the money.
But if you have money,
no, this methods needs big продолжение работы. Continue work, yes, and investigation, and what?
Success. I hope you success and really interesting. Thank you.
So thank you, Arseny. We should go to the next report from Evgeny Panin, our guest from Kazakhstan, Karaganda Industrial University. Evgeny, are you here?
Yes, I'm here. Hello, everyone.
You're welcome. We see your presentation. You're welcome.
Okay, fine. Well, let me present the work titled Mechanism and Patterns of Chromium Steels Wear with Surface Hardening under the Action of Pulsating Contact Stresses. The plan of the report, it's introduction, purpose of the work, materials and methods, results and discussion, and conclusion in the end. One of the most common factors limiting the time to failure of treatment tool is contact wear of its working surface. The intensity of pitting formation is determined by the level of tangential stress occurring in the sublayer, which cause micro deformation at the depth of 0.2 till 0.4 millimeters from the surface. The evolution of the surface layer structure includes the stage of formation of intercrystalline defects and their growth. One of the most effective ways to increase the contact endurance is the surface modification of the outer layer of the material, in which the depth of the hardened layer is obviously greater than the depth of which dangerous threats occur. For composite metal materials, which include diffusion hardened layers of the alloyed steels, the structural features of modified layer also play an important role in the mechanism of origin and development of contact fatigue cracks. Numerous experiments of the assessment of contact endurance, as well as their design verification, usually focused on the projection criterion for determining the limited state of damage and adapt to gears with an involute profile. So the relevance of the study is the fact that wear of the working layer allowed during the operation of the die tool, especially tool for stamping operations, requires obtaining information about the ability of the entire hardened layer at the depth of 0.5-0.6 millimeter. So the aim of the work is investigation of influence of contact wear of the surface layers of stamping steel formed at the preliminary stages of modification with subsequent quenching and tempering under the action of pulsating contact stress. The experimental evaluation of contact wear was carried out on the original equipment for testing materials for contact fatigue and wear. The construction of this stand is defended by Belarusian patent, and the main principle of this device is that in the left disc you can see increased image of this block. Four workpiece installed at the outer layer of discs. Here below there are tray with lubricant, and contact stress is formed by right disc named the loading unit. Here we have a stiffness spring that provide the linear speed of wall construction with a speed of 35 millimeters per second. Here you can see the main information about material workpiece, material of counterbody. Its counterbody is the right disc in this device. The a value of wear is estimated by direct measurement of wear crater that formed under loading by a DL indicator with an accuracy of 0.01 millimeter. The surface layer was modified by nitriding and nitrocarburizing. Thermochemical treatments mode were next. First, in the beginning, the saturation was carried out, and after that was done quenching and tempering. In the second mode, the surface layer was modified, and then after preheated samples were quenched and then tempering. At the first stage of investigation, it was studied the influence of tempering temperature. The quenching was done at a temperature of 1060 degrees, and tempering was done at two temperatures, 200 degrees and 525 degrees. Here you can see the result of these two modes. Estimation was done at the next principle when the value of wear reaches or ever exceeds the value of 0.6 millimeters. The experiment was stopped. So when we used quenching and tempering at 200 degrees, we reached about 9,000 loading cycles. But using more high temperature tempering reduce the number of load cycles up to 5,300 degrees. So at next stages of investigation, it was decided to use only tempering at 200 degrees, like low temperature tempering. Next stage of investigation for both batches of samples, it was also two different modes of saturation and thermomechanical treatment. As both nitriding and nitrocarburizing, in the first mode, first operation was saturation and then quenching and tempering, and at the second treatment mode, first was quenching and tempering, and then both type of saturation. As a result, it was indicated that using modes of saturation and then thermomechanical treatment allows to obtain more smooth reduce of microhardness until the depth of about 400 microns. Then, at the final stage of investigation, it was studied the influence of each type of saturation and it possible mode before and after thermal treatment. On the absolute value of wear dependence of number of loading cycles. In both cases, as for nitridine and nitrocarburizine, it was revealed that the most optimal condition is providing saturation and then only quenching and tempering. If we done quenching and tempering at the first level and then saturation, in both cases we had the wear value exceeds the critical value 0.06 about less than 5 thousandths in the case of nitridine and less than 10 thousandths in the case of nitrocarburizine. But in the saturation at the first stage and then quenching and tempering, we had really increasing of number of loading cycles before it reached the critical value. And in the case of nitrocarburizine, we ever didn't reach critical value before, because in the case of 25 thousandths loading cycles, we obtained the wear value about 0.5 millimeters. So in this case, we obtain different optical microscope images at the different stages of loading cycles. As you can see, after 5,000 loading cycles, there is no microcracks. After 10,000, we have only initiation of microcracks, and after 15,000 loading cycles, we had microcracks only at the rib of counterbody contact zone here. But in the almost wall width of counterbody, there is no visible cracks. So conducted studies of in the work revealed that thermomechanical treatments models with nitrocarburizine and quenching and tempering allow to obtain the hardening layer of investigated stamped steel, and it allows to use this mode or for hardening of stamping tool used in cold stamping operation. Well, thank you for attention.
Thank you, Evgeny, for your report. Colleagues, do you have any questions? I have a few. First of all, slide number 10. Could you show it? Right side, and if we speak about black line, both of them is black. how can you explain this ladder manner of
Step
query?
zones?
Yes, like лестница, да.
Well, we have discussion about such graph data, and in our opinion, it depends mostly that nitrocarburizing allowed to obtain the hardening layers that have multi-hardness layers, because in this case we have almost horizontal character of this curve, and because until, for example, here the outer layer, until these zones will be not destroyed under the contact stresses, the next zone will be not increased by value of wear. And here, for example, we have more smooth increased uniform increase the character of a curve. Here, nitriding allows to obtain more uniform hardened layer.
Okay.
We think that the reason in that, but future more deeply metallography experiments will show we are right or we are don't right.
And also, I think you plan to make some computer simulation of such process, because
yeah, we discussed really about this, but we need before this to make maybe more mechanical testing investigation, because of, as you know, usually the form can simulate uniform material with, for example, if at zero stage we don't have any stress, strains, and we have that value of stress that includes in the material database. But for example, in the form, there is a future to simulate the material with coating. Mm-hmm. And if we will have mechanical characteristics of this hardening layer, for example, at each 10 micrometers, so we will be able to create workpiece with multi-coatings.
Because it's my opinion, because it will be really interesting, and you can receive a lot of data about residual stress, about wearing of tool, and so on and so forth.
Yes, you are right, but in this case we need before computer simulation to collect more data about mechanical properties.
Okay, thank you. So we should go to. Thank you for your report. We should go to the next report from Central South University, China. Professor Gao, are you here?
Yeah, I'm here.
We hear you. Or you can start. You can demonstrate your screen.
Thank you.
We see your presentation. You're welcome.
Thank you. Good afternoon, everyone. My name is Gao Haitao from Central South University, China. My advisor is Professor Yu Hailiang. Before starting my presentation, I have some words in memory of Professor Alexander ZHILYAEV. I still remember in 2019, Professor ZHILYAEV came to China and gave us an excellent speech. I was deeply impressed by his wisdom and kindness, and I am sure that his spirit will inspire the followers forever. The title of my presentation is Microstructure and Mechanical Properties of Copper Aluminum Clad Sheet Processed by the Powder-in-Tube method. The main contents include 4 parts: background, experimental procedures, results and discussion, and the last part, conclusion. First, please let me introduce the background. Copper aluminum composite materials are widely used in the fields of electrocommunication and aerospace, whose main forms include sheet, wire, and joint. The design principle of copper aluminum composite materials is the skin effect of electric current. There are 2 obvious advantages for copper aluminum composite materials. One is reducing the usage of copper and fabrication costs. The other is losing weight more than 60%. The traditional fabrication methods for copper aluminum composite materials are roll cladding and cast roll cladding. The schematic diagrams of their fabrication process are exhibited as follows. The advantages of roll cladding are simple price, high production efficiency, flexible control of IMC thickness. At the same time, there are still some obvious disadvantages. For example, the large reduction ratio in the first pass is necessary to obtain the ideal bonding quality, which results in the high equipment capability requirements and high input cost. In contrast, copper aluminum composite materials fabricated by the cast rolling cladding show the higher bonding strength and shorter fabrication process. However, the cast rolling process causes low production efficiency, high energy consumption, and difficult regulation of IMC. Powder-in-tube method is originally applied in the fabrication of superconducting wire or strip. In recent years, it is implemented in many other fields. For example, Reject fabricated the foam aluminum-filled tube to improve the actual compression performance of hollow tube. Zhang produced the iron chip stainless steel clad sheet with the favorable bending ductility. You prepare the high-performance carbon nanotube copper composite sheet by combining the asymmetrical rolling and powder-in-tube method. Our team fabricated the blast furnace slag-filled tube, which can reduce the usage of steel and provide a new way to efficiently use the blast furnace slag. The fabrication process of copper and copper aluminum clad sheet is provided as the left picture. Compared with the traditional cladding method to prepare copper aluminum composite materials, the obvious advantages of powder-in-tube method are simple process, low equipment capability requirements, high production efficiency, and less pollution. For traditional fabrication methods, the large deformation in the first rolling pass is necessary to make the oxidation film broken and defect closure. On the contrary, the powder in tube method turned the bonding form from face to face into point to face, which reduces the difficulty of interfacial bonding and results in the high bonding quality. According to the SEM images of bonding interface, obvious copper and aluminum IMC layer can be clearly observed. Moreover, the thickness of IMC layer increases with the annealing temperature. Further rolling makes the IMC layer become thinner and disturb its constitutivity, especially for the clad sheet. Annealed at 550 degrees centigrade, thick IMC layer is formed at the bonding interface and completely broken under the large rolling pressure. The slag of IMC are pressed into copper and aluminum magazines. From the results of elemental diffusion at the bonding interface, we can see that interfacial diffusion is relatively weak at the low annealing temperature of 350 degrees. As with the increase of annealing temperature, the energy obtained by the copper and aluminum atoms exceeds the diffusion barriers and promotes the formation of IMC. The detailed case of IMC at the bonding interface are shown as this figure. Further rolling makes IMC layer broken and its thickness decrease. To test the bonding strength of copper and aluminum clad sheet fabricated by the powder in tube method, T-type sample is designed as the following imagine. With the increase of annealing temperature, the peeling stress of copper and aluminum clad sheet firstly increased and then decreased. Further rolling makes the peeling stress obviously increase. The largest peeling stress of around 18 Newton per millimeter is obtained for FR 480 compared with FR 318 and FR 518. The thickness of IMC layer is relatively moderate, which becomes denser in the further rolling process and leads to high peeling stress. For the sample annealed at 450 degrees, there are no cracks or pores on the peeling surface. Instead, scale-like IMC layer and a rough surface can be observed. The main IMC at the peeling surface is copper aluminum two-phase. After further rolling, the initial scale-like IMC are turned into dense and continuous blocks. The main IMC is still copper aluminum two-phase, accompanied by the little increment of aluminum matrix. The engineering stress strain covers of copper aluminum clad sheet is displayed as the following image. FR 4,150 exhibits the largest tensile stress, elongation, and uniform deformation, which is beneficial from the formation of moderate and dense IMC layer. While for FR 315, the interface debonding occurred in the test. While for FR 450, the IMC are still connected with copper and aluminum matrix, leading to the high strength and ductility. As to FR 550, obvious interfacial crack is formed in the tensile process, and IMC are almost totally peeled from the matrix. The last part is the conclusions. Copper and aluminum clad sheets were produced successfully using the powder in tube method, which can significantly improve the metal yield and simplify the production process of clad sheets. For the cold rolling process can significantly reduce the thickness of intermediate layer and improve the average peeling strength of copper aluminum clad sheets. The final peeling strength for clad sheets with different annealing temperature are 11, 18, and 3 Newton per millimeter respectively. Copper and aluminum clad sheets annealed at 515 degrees process the largest tensile stress and elongation in the tensile test. In the deformation process, interface debonding occurs in the clad sheets for FR 350, and the IMC layers of FR 515 are broken. Only the clad sheets annealed at 415 degrees can retain a complete and continuous IMC layer due to the formation of compact and uniform IMC layer. That's all. Thank you for your attention.
Thank you for your report. Colleagues, do you have any questions?
Ask just a small question.
You're welcome.
This method could be applied only for two components composites. I mean, did you try, for example, put not only alumina powder, but some kind of mix with, I don't know, magnesium, for example?
Thank you for your question. Yeah, this method have been applied in many other field except superconduction wire.
Thanks.
And also, in addition to previous question, this is just for discussion. What do you think? Is it possible to scale this process to industrial application for massive production, or this process has some limitations at this moment?
Thank you for your question. This method have achieved industrial application in Jiangsu province of Wuxi. The master limitation is how to match the input of aluminum powder and the process speed. This is difficultly to control.
Okay, thank you. And what is the biggest size of billet or samples you can achieve in industrial? Maybe you know, in industrial field. What is the biggest size of ship?
The biggest, the weight of this class sheet now we can produce as weight as 150 millimeters.
Okay. I satisfied. Okay, thank you.
Thank you very much.
Colleagues, do you have any questions?
Yeah, Dmitry, can I ask one question?
You're welcome.
Yeah, thank you for such interesting presentation. I would like to clarify about the failure after the high temperature annealing at 550 degrees. As you said, that is caused because the interfacial failure.
Yeah, thank you for your question. When the new temperature increase to 550, the size of IMC will become large and will broken in the rolling process, in the further rolling process, and peeled from the copper and aluminum matrix, resulting in the decrease of the peeling stress.
Okay, thank you.
Thank you for your question.
So thank you for your report. And next report goes from Belgorod State University, from Anna Bodikova.
Good day.
Do
you hear me?
Yes.
Okay.
One moment, please. You can share your screen.
Yes.
And we see your presentation. You're welcome.
Thank you. Good day, dear colleagues. My name is Bodikova Anna. I am a researcher in the Laboratory of Mechanical Properties of Nanoscale Materials and Superalloys in Belgrade State University. The topic of my presentation is the effect of chromium content on dispersion strengthening of copper, chromium, zirconium alloys. Copper alloys and copper and its alloys after severe plastic deformation was the topic jointly research of our team. We included Professor ZHILYAEV, Roman Mishnin, Yaroslava Shachova, Andrei Belikov, and Rustam Kaybyshev. Our published articles focused on the microstructural evolution, strengthening and wear resistance during ECAP in copper and copper, chromium, zirconium alloys. So this presentation is the extension of this research. The copper, chromium, zirconium alloys exhibit high strength and high electrical conductivity. They are widely used in various electronic devices due to a good combination of mechanical and physical properties, which can be achieved by conventional heat treatment, consisting of solution treatment followed by aging. Despite several works devoted to examining the phase composition in copper, chromium, zirconium alloys after aging treatment, the crystal structure and phase stoichiometry remain a subject of some debates. So this work aims to clarify the phase composition in two-ternary copper, chromium, zirconium alloys with different chromium contents, and estimate the contribution of fine dispersoids to the yield strength of copper alloys with various contents of chromium. Two alloys, copper 0.1% chromium, 0.1% zirconium, and copper 0.9% chromium, 0.1% zirconium were investigated. The solution treatment was conducted at a temperature 920 degrees of Celsius, followed by water quenching. Several samples were subjected to aging. The hardening was studied using Fresnel hardness test. The electrical conductivities of samples were measured by eddy current methods. The mechanical tests were conducted at room temperature. The precipitates and fine microstructure of samples were characterized by a transmission electron microscope. The microstructure of copper alloys are presented by grains with average grain size of approximately 12 micron in 0.9 chromium alloys and 125 micron in 0.1 chromium alloys. The fine microstructure of 0.9 chromium alloys consists of several coarse chromium and zirconium-rich particles with size above 200 nanometers. In contrast, any coarse particles were not observed in 0.1 chromium alloys after solution treatment. Figures show the changes in hardness and electrical conductivity as function of temperature during 1 hour aging. The hardness increases significantly with temperature in the range of 300 to 450 degrees Celsius for 0.9 chromium alloys. The hardness maximum of approximately 92 Brenner hardness was observed after aging at a temperature of 475 degrees Celsius. Then the hardness significantly decreased. Similar behavior of the hardness change was observed for the 0.1 chromium alloy. The hardness reaches a maximum of approximately 67 Brenner hardness after aging at 550 degrees Celsius. An increase in the aging temperature leads into a gradual increase in the electrical conductivity. Note here that in 0.1 chromium alloys is surprised by the least electrical conductivity in temperatures of 400, 500 degrees Celsius, despite the highest electrical conductivity after solution treatment. The influence of the aging time on the hardness and electrical conductivity of copper chrome zirconium alloys are presented on the slide. Following an increase to a maximum, the hardness of the 0.1 chromium alloys slightly decreased, approaching some saturation value with increasing the aging time. Increase in the aging temperature from 450 degrees to 550 degrees Celsius shifts the peak hardness to a shorter annealing time. The hardness curves for the 0.9 chromium alloys are characterized by almost the same shape. Aging leads to reaching the hardness maximum of about 100 Brenner hardness irrespective of the aging temperature. Aging at 450 degrees is accompanied by gradual increase of electrical conductivity in 0.1 chromium alloys, but electrical conductivity in 0.9 chromium alloys after 8 hours achieve 90% of electrical conductivity of pure copper and then saturated. The same aging behavior of electrical conductivity in 0.1 copper alloys is observed after high temperature. The strain stress curves for alloys are characterized by repeat strain hardening during early deformation. In solution-treated conditions, the 0.9 chromium alloy exhibits higher ultimate tensile strength of approximately 240 MPa compared with 190 MPa for 0.1 chromium alloys. The aging treatment of 0.9 copper alloys result in more than 100 MPa increments in the strength. The aging treatment of the 0.1 chromium alloys does not result in such remarkable change in the tensile properties. The increments consist of about 60-80 MPa. The decomposition of solid solution in 0.1 chromium alloy does not obtain after 1 hour aging. An increase the annealing time to 4 hours result in formation copper-rich chromium FCC chromium particle with coffee bean contrast and size about 5 nanometer. After 16 hour aging, the elongated BCC chromium particle are observed. The longitudinal size of BCC chromium particle achieves 7 nanometers, transverse 6 nanometers. The zirconium-rich particles with hexagonal lattice are observed in the 0.1 chromium alloys after 24 hours of aging. The detailed chemical analysis of the individual BCC chromium particles in the peak edge state at temperature of 550 degrees Celsius is demonstrated that the chromium and zirconium atoms are concentrated within particles while chrome depleted the matrix. The product of decomposition of solid solution after aging at 450 degrees Celsius and 500 degrees Celsius obtained for 0.9 chromium alloys are shown. Numerous tiny, almost spherical particles with average size of approximately 3 nanometers and copper bean contrast are homogeneously distributed in the copper matrix after aging at 1 hour. Corresponding diffraction patterns relieve individual reflex from BCC chromium lattice typical for Nishiyama-Wassermann rotation relationship, early stage of chrome particle precipitation. Prolonging the aging at 450 degrees Celsius result in negligible course of chromium dysprotsoids to 4 nanometer after the aging for 16 hours. Aging at 500 degrees Celsius leads to precipitation of BCC chrome dispersoids with Nishiyama-Wassermann rotation relationship and elongation shape. Many relatively coarse primary particles are observed in the aged 0.9 chromium samples. The coarse particle can be grouped into two categories, depending on chromium and zirconium content. There are chromium particles containing small amount of zirconium, below 20%, with spherical shape, and the particle size above 100 nanometers, and elongated particles containing the equal atomic fraction of chromium and zirconium with lengths above 1 micron. This phase stoichiometry is similar to the Heusler phase. The particles number density in the 0.1 chromium alloys increase gradually with the aging time after an incubation period of about 1 hour. In contrast, many dispersed particles with coffee bean contrast form in the 0.9 chromium alloy after 1 hour aging, and further aging not influence particle number. The particle stability against coercion depends remarkably on the chromium content. The size of fine chromium particle in the 0.9 chromium alloys does not significantly depend on the aging temperature and time. A rather large value of the particle growth exponent, about 12-15, is observed. In contrast, the size of the chromium particle in the 0.1 chromium alloy faster increases during aging. The particle growth exponent decreases from 3 to 2 as the aging temperature increases. Decomposition of solid solution in conductivity material can be expressed by a sigmoidal relationship. Professor Matheson proposed to describe the composition of solid solution using electrical resistivity. So conversion of this equation leads to follow relationship that illustrated in figure. All experimental points are well approximately biline law. There are 3 lines law associated with nucleation growth and particle growth. 0.1 chromium Lewis is characterized by a prolonged incubation period and low number density of particle corresponding to this region in the relationship. Note the nuclear and particle growth is larger in 0.1 chromium Lewis. Moreover, higher saturation of solid solution results in smaller critical particle size as 5 nanometer and 3 nanometer for the 0.1 and 0.9 chromium Lewis respectively. The prolonged incubation period, lower number density, large particle size of chromium particle in the 0.1 chromium Lewis can be explained using the driving force. With this relationship, the concentration of alloyed elements in the solid solution controls driving force, determined nuclear rate, and critical particle size. According to this equation, driving force in the 0.1 chromium Lewis is less in about 24 than in the 0.9 chromium Lewis. Some critical particle size is inversely proportional to chromium content. The minimum particle size of chromium particles observed in TEM is about 2-3 nanometer in the 0.9 chromium Lewis. Such particles should have coherence interface boundary due to low misfit parameters. In contrast, the critical and observed size of chromium-rich particle in the 0.1 chromium Lewis is larger, about 5-8 nanometer, and should have semi-coherent interface boundaries. Moreover, the kinetic of nucleation growth and subsequent Ostwald tripping predict high particle growth in 0.1 copper Lewis. High initial critical particle radius and small initial concentration of chromium in the matrix of the 0.1 chromium Lewis correspond to high growth kinetic of nucleation. Other hand, Ostwald tripping is controlled by interface energy of particle. The high energy of semi-coherent interface boundary in the 0.1 chromium promotes the coarsening of chromium particles. Stabilizing particle in 0.9 chromium is provided by high nucleation rate and low kinetic particle growth, which is determined by a coherent interface boundary with low energy. In general, the yield strength of dispersional hardened metallic materials can be estimated by modified whole page relationship. Regarding the contribution to the mechanical properties, the major role is played by the fine particles. The nanoscales and dispersor plays a role as obstacles for the movement of dislocation. There are 2 types of interaction between particles and dislocation. One of them is the known Oravan mechanism, when the dislocation produces loops around the precipitates. The Oravan equation gives closer calculation values of yield strength to the experimental data for 0.1 chromium Lewis aged at various temperature. However, there is a significant deviation of the calculation values from the obtained values for 0.9 chromium Lewis. So the mechanism of precipitation strengthening for 0.9 chromium should be different. The other type of interaction is the sharing of the precipitation by dislocation, included coherency strengthening and modulus strengthening. The yield strength of 0.9 chromium alloy is reasonably consistent with the experimental data. In contrast, the application of the sharing mechanism to 0.1 chromium alloys result in overestimate values of the yield strength. Therefore, the sharing mechanism of precipitation strengthening can be applied for 0.9 chromium alloys with tiny chromium coherent particles, but not for 0.1 chromium alloys with relatively coarse particles with semi-coherent interface boundaries. In conclusion, I'm going to say that the size of second phase particles and strengthening mechanism depended remarkably on the chromium content. The strengthening of the copper 0.9 chromium alloy in the peak edge condition was mainly attributed to uniform dispersion of tiny chromium-rich particles with size of 4-5 nanometers, which could be overcome by moving dislocation through sharing. In contrast, the microstructure of the peak edge condition of the copper 0.1 chromium alloy was characterized by the dispersion of relatively large chromium particles with size of about 8-10 nanometers, which result in strengthening accordingly R1 mechanism. Thank you for your attention. If there are any questions, I will be glad to answer.
Thank you, Anna, for your report. Colleagues, do you have any question?
Yes, Dmitry, may I ask one question?
You're welcome.
Yes, thank you, Anna, for such interesting presentation. I have a small question about the zirconium addition. What's the purpose of this addition in this alloy? What's the role?
That zirconium can promote precipitation more particles. In literature, there are information about copper zirconium particles, and we show that zirconium segregate on chromium particles. So we alloyed zirconium for strengthening, additional strengthening of copper chromium alloys.
Yeah, did you compare the properties of the alloy without the zirconium to confirm its influence?
In my work, we didn't make this research, but when we can see in literature, the alloy with zirconium have highest strengthening than copper chromium alloys.
Okay, thank you.
Thank you. Colleagues, do you have any question? I have a few new big questions, which just for me. I paid attention on slide number 7. Right side. Does it mean that at some condition there is no difference between two alloys? For example, the one black line is totally the same as the green line.
In this regimes?
Yes.
It is because all chromium and zirconium atoms precipitate in particles, and the matrix is depleted of alloyed elements, so the electrical conductivity in these regimes is the same.
Yeah, okay. And slide number 15. About mathematical equations. On the right side, you have equation multiplied by 0.0055, but it's too small. Is it some constant or something what?
So it's not my equation. I use equation of Lavergne. They have this equation. I can send you an article maybe, if it's interesting for you.
Professor Stolяров, do you have any question?
No. As for me, no. I have no question.
No, thank you. So,
can I ask one question?
Of course, you're welcome.
Hello.
Yes, you can ask.
Can I ask you one question? I'd like to ask about solubility of chromium and particular zirconium in copper solid solution at aging temperatures. What is the value of solubility?
The value of solubility, maximum solubility of chromium is about 0.6, 0.7.
At aging temperatures?
Yes. No.
I mean aging temperatures.
At aging temperatures is about 0.05.
And zirconium?
And zirconium 0.02.
So it's much smaller than 0.1, your concentration. Yes. Thank you.
Yes.
So, colleagues, thank you. We shall go to the next report from. Thank you, Anna. For the next report from Professor Pesin again. And please switch on your microphone. Professor Pesin.
Yes, I will.
We see your presentation. You're welcome.
Yes. The theme of my presentation is development of asymmetric rolling technology as a method of severe plastic deformation. I'm sorry that Associated Professor Pustovoytov should be here, but he is ill, and I will make this presentation, but it's of course our presentation. And I think that when we use SPD methods, we have two main problems. The first problem for sheet production. The first problem is fundamental. It's low ductility. As usual, we increase strength, but decrease radically ductility. And of course, it's famous. And the second problem, it's the same famous, that it's very difficult to find methods to produce sheets and strips using SPD methods. Of course, there is a roll bonding and so on. And but in every SPD methods, they use one of the main thing is shear strain. And if we compare ECAP and conventional rolling process, you could see that in ECAP we have simple shear, and conventional rolling we have poor shear. And of course, if we speak about application in industry, we need to get a continuous scheme. It's rolling, drawing, and maybe stamping. It's not continuous, but it's a very productivity process too. And of course, I have no time. Of course, that now we have very asymmetrical rolling mill. It's possible for us to have reduction with steel in one pass for about maybe 65–80% for steel. And again, the characteristic of the rolling mill you could see. And it's possible to combine. The idea is to combine two kinds of shear strain. You could see that in ECAP it was simple strain. Is it okay in my presentation? I'm sorry.
We see only the first slide.
The first slide also. I'm sorry because I show you many slides. You have no changing, yes, in your.
Yes.
I closed and.
Попробуйте перезапустить
демонстрацию. And
Все, листается.
It's okay, yes?
Да.
And I told you that in a cup and conventional rolling, we have a different kind of shear strain. And the task and the idea is to combine, to accumulate both kinds of shear strain. And I told you about new rolling mill. Okay, continue. And one of the idea is to use asymmetrical roll. In Soviet Union and in Western countries, there were many publications, there were many scientific schools, but it was until the end of the 90s years, maybe at the beginning of the 1990s, it was finished. The main school in Russia was in Chelyabinsk. The head of this school was Vidrin, but you could see that at the beginning of the 10th years of this century, it began to grow the quantity of publications, and it's a renaissance of the interest to this process. Why? Because before the 10th years, nobody wanted to control texture and did not think about grain size. Of course, think about mechanical properties. And they did not use the coefficient of asymmetry more than 2. And you could see, I have no time, we could see the many publications, and you could see for years that at the beginning of the 90s, there were few publications, and now it's nearly okay. You could see the quantity of publication for by country. The most quantity of publication is in Korea. There is centers in Korea which are studying in this process. The second center of now is in China. You could see the centers of asymmetrical rolling in China and Japan. You could see the centers here. And in Russia. And you could see that in simple share, you could see how to deform the circle, and you could see there is the same process is in the cup and poor share during convenient rolling. And in asymmetrical rolling, you could see that we have changing, combine both this process. And if we have equivalent strain during asymmetrical rolling, the formula, and if we have poor share, we can get conventional roll. If you have simple, you can get EK process. The main thing which we can get is that we find the area. When we try to find influence between shear angle, it's one of the main parameters in SPD process, and equivalent strain, shear strain deformation. You could see that, for example, conventional rolling with deformation 60% is here, the point. One pass EK process is here, and 4 pass EK is here. And if we have big deformation, more than maybe 90% in one pass, and you have a very big friction, I will speak about it, you can get, you can be here in this field for one pass of using a symmetric roll. You could see that single pass and symmetrical rolling can give some gradient, but not so big. You have that 2.75 in surfaces, and in the middle about 1. But this is a big reduction. But when you use a symmetrical rolling, the vertical cross section toned, and it's possible to tone for 80, maybe about 80 degrees, and vertical cross section could be near horizontal after the rolling. You could see here that if we have a very big friction, it's problem, real problem. You can get 6.8 in surface, and about 4 in another surface, and equivalent strain up to more than 4 in one pass. But you could see the mechanism of this process, that ellipsoid, the circle begins to ellipsoid, and then turn radically for more than 80 degrees. We found optimum, because the difference between roll speed should not be very high. It should be a bit less than reduction. And we could see that everywhere we can get it. And you could see the gradient of the in the effective strain. Here you can compare asymmetric and symmetric rolling. I will speak about here theoretical decision and strain distribution. The same. Now we are working. About months ago, we start to work with our rolling mill. Now we have some results I will show you. Of course, it's very difficult to increase the coefficient friction conditions. And in our research, we show that if we have normal conditions, friction conditions, about 0.1, 0.15, maybe 0.2 coefficient of friction, we can't get a big difference between symmetrical and asymmetrical processes. We have the difference began from the big difference in friction coefficient of friction, and we have some problem. Of course, it's possible to find the decision, and we can do it. That if we increase radically coefficient of friction, we decrease the quality of surface. Maybe for some materials it could be limitation, because it will be a big increasing of temperature. But for some of them, for some materials, it's good. For example, for some kinds of aluminum, it's critical situation. But for another kinds of a series of aluminum, it's okay. It may be big plus, and we have the same research. I have no big time, but we have research with a
few minutes
bimetals and 3 metals, and we have the first results. Of course, I think that in a month we have much more results for many metals, but now we use this copper. We have 3 package from 3 sheets with thickness 2 millimeters, every of them, and the final thickness of package was 1.74.
Professor Petin, may I ask Evgeny Arushensky, are you here? If we don't have next report, you can continue. Because I don't see him in chat. And if we don't have a report from Samara National Research University, you can continue. I think we have a gap in schedule. That's why you can continue.
Okay, thank you very much. And you have in this figure, you have a general view of cross section of layers, the package after the rolling. And you could see the structure from the side of the roll, which with a higher speed. It was 6 meters per minute, not second, per minute. I'm sorry, it's mistake. Experimental, and you could see that from the side of roll, the same with the roll, with a low speed. And in the first variant, we have a structure with the it's about 1 micron, and from the bottom surface it's about 5 micron, and you could see the differences. It's interesting that there is many I don't know, двойники, twins, deformation twins, up to about 500 nanometers. But maybe you could see it's our first results in experimental. I think that we can. I repeat that we have to. I think that in a month, in 2 months, we'll get many experiments and have to get good many results experimental. And now we have collaboration with several universities, and we have possibility to maybe if you have some sheets, some materials, we can treat them. We can organize rolling with big reduction in one pass, and maybe with several passes with big reduction, and maybe it will be interesting for you. No, and for us. Thanks for attention. I think that we have now as a conclusion, I have to say that we have many results in theoretical field. We have interesting results, but now we have to prove them experimentally. And I think that we can get it, but in short time.
So thank you for your second plenary report in general, or if we speak about time limit. So colleagues, you can ask your question. You're welcome.
Can I ask?
Of course, of course.
Dear Professor Pesin, thank you for your excellent report. It's very interesting for us. Can you say something about properties of materials that you received? What is the main reason for production of such materials?
To produce such materials, only one reason, because we can get gradient structure, because the difference between strain on this one surface and other very big. And as we see for the first results, there is a differences in sizes of the grain sizes, and to our understanding, it should be differences in structure at all. If we can get this difference, I think it's interesting. We understand that it's not needed. Our industry not needed to produce million tons, but maybe it could be produced, it would be organized maybe to buy or build the rolling mill, asymmetrical rolling mill, and produce maybe our iron steel could produce several thousand tons for our country. Maybe it will be enough for us. but it will be.
And what about properties?
Properties, we can get properties. We begin to measure hardness of the surfaces. Hardness in the difference in hardness in our experiment was about 20%. But I think that it's we have no enough. Our friction was low. The level of friction was low, and now we are working under the increase in friction. And I think that now we can get that there is differences there is, but it's I think that it should be radically more.
Okay, thank you.
So, colleagues, more questions?
Just one.
Daria, you're welcome.
Okay. Thank you for your wonderful report, Professor Persson, and I congratulate you with this equipment. You was waiting so long. So I have just small questions. Correct me if I'm wrong. Are you right now? You provide experiments only at room temperature? I mean, rolling.
No, we can provide the experiments. No, this experiment, yes, was in room temperature, but we can use warm rolling, and I think that this year, maybe in several months, we can get equipment for increasing the temperature of rolls, for producing special materials which needs short diapason of the temperature in treatment.
You mean increase at higher temperature, yeah?
For about maybe 400 degrees, we can increase the temperature of rolls.
Okay, and what about, I don't know, cryogenic deformation?
Sorry?
Cryogenic, I mean, what about to decrease temperature, to perform cryogenic deformation?
We can do it. We can do it cryo-rolling.
Okay, thank you.
We have not done yet, but we can do it. Maybe it's next step. Not now, because now we have so many tasks in room temperature. And of course, when we use asymmetrical rolling, the temperature, the deformation is too big, and we have increase in temperature. For example, for 300 degrees, if possible, or 400 degrees. And now we have some sheets, from Professor Belov, I'm sorry, from Professor Belov, and for his aluminium, kind of aluminium, it's better to have increasing temperature till maybe 500 degrees, and we can understand what will be happen.
And another one, maybe I missed it. What's the size of the samples you wrote? The size?
The width 400.
Mm-hmm.
It's maximum. No, not 400. It's 380.
Mm-hmm.
And for we try to use automobile sheets from 0.5 millimeters. The finishing for finally thickness, and till maybe we have no
limit.
Have no limitation, because the possibility of moving our roll is about more than 100.
Okay, thank you.
We can take, of course, it's not so quick, but we can take your sheet with maybe 10 millimeters, roll in it, then using special treatment can continue till the size. We have no limitation.
Okay, thanks for your.
Thank you for your report. I want to invite Professor Belov from National University of Science and Technology, Mrs. Professor Belov, if you want, you have extra time for your
Yes, I'm
report.
here.
Yes.
I'm trying to set my presentation. What should I? Do you see my presentation?
Yes.
Yes. And do you see the second slide?
Yes.
Yeah, okay. Good afternoon. My name is Nikolai Belov. I am from National Research and Technology University, MSIS, Moscow. And this presentation entitled Effect of Cold Rolling and Annealing Temperature on Structure Hardness and Electrical Conductivity of Rapidly Solidified Aluminum Alloys was given composition, prepared together with my colleague from Moscow University and with Viktor Timofeyev from Krasnoyarsk. My presentation consists of three main parts. First, introduction focused on electromagnetic casting technology. Second, principle of designing of a heat treatment alloy on the base of aluminum, copper, manganese, zirconium system. And third, main part, structure and properties of alloy, aluminum, 3.3 copper, 2.5 manganese, and 0.1 zirconium manufactured by EMC method. Introduction. History of heat-resistant aluminum alloys. It's well known that aluminum-copper alloys possess best combination of mechanical properties at room at elevated temperatures. That there are two significant lacks of these conventional alloys. First, they need technology including homogenization for ingots and quenching and solution treatment for road products. And the second lack is limits of working temperature, approximately 250, because at high temperatures, precipitative of aluminum to copper phase cause an end. Some decades ago, it was proposed to design alloys with increased amount of transition metals, particularly zirconium, manganese, and this method was called ICPM, that means rapid solidification and powder metallurgy. But this is a very complicated technology, and final products are very expensive. So this technology are not used at present time. As alternative, we proposed to develop aluminum alloys with high amount of transition metals for method of electromagnetic casting. This method provide casting at a sufficiently high temperature, up to 900 degrees centigrade, and very fast solidification, over than 1000 Kelvin per second. That means the same for technology ISPM. So it's possible to realize the same structure, but much more cheaper. The principal scheme of EMC shown in the slide. The main parts of this technology is furnace with aluminum melt and electromagnetic crystallizer, which provide extra rapid cooling during solidification. Existing equipment we used was designed and located in Krasnoyarsk, in the center of magnetic hydrodynamic. The product of this technology is continuous cast rod, this spool of this ready-made 2 millimeters diameter rod, and this product is very suitable for wire production, the same as wire rods used for production in conventional technologies. This equipment was successfully used for manufacture of aluminum alloys with increased amount of zirconium. It's well known that aluminum alloys with zirconium have excellent combination of strength, electrical conductivity, and thermal stability, but conventional technology may be used only for alloys containing up to 0.3–0.4% of zirconium. Detailed information about these results may be found in papers given in this slide. So our next stage to produce alloys with increased amount of zirconium. Because we consider such alloys as the most creep-resistant alloys compared with all known aluminum alloys. The idea of alloy design for EMC technology consists of three main items. First, to realize in a cast rod of this quaternary system near single-phase structure, that means with minimal amount of eutectic particles, aluminum to copper, and full dissolving of manganese and zirconium in aluminum solid solution. Second, to realize and deform products, particularly in wire strips and so on, the structure with high amount of dispersoid, particularly ternary compound aluminum 20 copper manganese, and aluminum 3 zirconium, I mean cubic metastable phase, instead of aluminum 2 copper precipitators, which take place in conventional aluminum copper alloys. And third, to propose energy efficient technology for such alloys without homogenization, solution treatment, and quenching process. Details may be found in papers given below. This idea may be illustrated by phase diagram of aluminum copper manganese system, where shown on position of conventional alloy 2219 with high amount of copper and small amount of zirconium. We propose to decrease copper content and increase manganese content to produce structure with maximal amount of ternary phase. To dissolve, and what is very important, this phase should be fully in form of dispersoids with minimal size, desirably below than 100 nanometers. To produce zirconium nanoparticles, zirconium should be dissolved in aluminum solution during solidification, and casting temperature should be above liquidus, because if temperature should be if temperature will be at below temperatures, or cooling velocity will be insufficient, primary crystals of aluminum zirconium 3-phase will form during solidification, so the structure unsuitable. These principles were successfully realized on the example of alloy consisting 0.55 copper and the same content of manganese and 0.0 zirconium. It was found that such composition possesses excellent combination of strength, electrical conductivity, and thermal stability up to 400 degrees centigrade. To increase manganese content, it's necessary to consider another technologies. That means electrical magnetic castings. We used existing equipment. The composition of used alloy given in the slide. This composition was selected according to phase diagram to provide maximal amount of ternary compound, and at the same time minimal concentration of zirconium at aluminum solid solution. This alloy was produced by method of AMC in form of 8 millimeters in diameter rod, and then it was directly cold rolled into the strip with thickness 2 millimeters. And the strip was the main subject of the investigation. This slide demonstrates the structure formation during solidification. In case of slow solidification, modeling using shale globule simulation show formation of primary crystals aluminum-3 zirconium and aluminum-6 manganese. And structure after slow solidification confirms this modeling curve. But in case of AMC structure, fast solidification suppress formation of these primary crystals, and all content of zirconium and manganese enters in aluminum solid solution. Copper distributes approximately 50-50 between aluminum solid solution and eutectic particles, aluminum to copper. Such structure is very suitable for cold deformation without any preliminary annealing. We used multi-step annealing starting from 200 degrees centigrade and up to 600 centigrade with step 50 degrees centigrade and holding 3 hours on each step. During certification, dispersoids of manganese phase and zirconium phase should form from a supersaturated solid solution. Concentration of these elements in aluminum solid solution should change according equilibrium we calculated in thermocalcs, and we may see that fraction of manganese containing zirconium is very high, about 10%, comparable with those for conventional aluminum alloys of 2000 series. But this precipitators is very stable compared with aluminum to copper precipitators. After annealing above 400 degrees centigrade, aluminum copper eutectic particles fully dissolved in aluminum solid solution, and dispersoids of ternary compound form in from supersaturated solid solution. And if temperature will increase, the size of these precipitates will increase also, but we need the size below than 100 nanometers, so temperature should be below. Fine structure of S-cast rod provide excellent deformability by cold rolling. Moreover, during deformability, aluminum to copper eutectic particles fragments into smaller inclusions, and after annealing, these inclusions dissolved in aluminum matrix, and precipitators containing manganese and zirconium form during annealing. At 400 degrees centigrade, this temperature seems optimal. The size of aluminum zirconium particles is about 10 nanometers, and size of manganese containing dispersoids is about 100 nanometers. But number of manganese containing particles is much higher compared with aluminum zirconium particles. Structure is fully unrecrystallized. And annealing increase hardness of initial S-cast rod because formation of aluminum zirconium 3 nanoparticles. These nanoparticles form at temperatures above 300 degrees centigrade, and this particle prevent recrystallization in cold rolled strips up to 400 degrees centigrade. At the same time, electrical resistivity decreased sharply during decomposition of aluminum solid solution, and it becomes suitable for electrical applications. If we compare alloys with different concentration of manganese, we may see that alloy with increased manganese content, that means experimental alloys of this study, the hardness is much higher. The difference is about 40 Vickers units. At the same time, electrical resistivity is approximately the same. It may be explained that in case of increased manganese content, the fraction of manganese containing dispersed fluid is higher, approximately on 3%, and concentration of manganese, copper, and zirconium in aluminum solid solution is approximately the same for both alloys. It's well known that any alloying increase electrical resistivity compared with pure aluminum. But elements containing in aluminum solid solution have much more negative effect on electrical resistivity compared with insoluble particles. We proposed equation for electrical resistivity, where Q is fraction of aluminum solid solution, here 0 electrical resistivity of pure aluminum, and other parameters of this equation are concentration of elements in aluminum solid solution and coefficients of their effect on electrical resistivity. And this plot shows that is a good agreement between experimental blue values and calculated red values at 450 and high temperatures. At lower temperatures, experimental values of electrical resistivity are higher. It may be explained that diffusion at such temperatures during 3 hours is insufficient to reach equilibrium concentration of alloying elements in aluminum solid solution, particularly of zirconium, having the minimal diffusion in aluminum solid solution. So we calculated the time to reach equilibrium solubility of all elements in aluminum solution at various temperatures using known coefficients. Here we found that at temperatures above 400 degrees centigrade, it's necessary some hours to reach equilibrium. At 400, it's necessary 12 hours. At 350 degrees centigrade, it's necessary 400 hours, and it's close to experimental values obtained on aluminum zirconium alloys. At lower temperatures, the time to reach equilibrium solubility is extra long out of practical application. So the temperature range between 450 and 400 degrees centigrade, this range is optimal to reach the optimal combination of desired properties. And summary shown in the slide draft, the method of electromagnetic casting is very promising technology to produce aluminum alloys with increased amount of transition metals, particularly manganese and zirconium. And this technology is very suitable for wire applications. first of all, for conductor, where where it's necessary to reach the maximal combination, the best combination of strength, electrical conductivity, and thermal stability at temperatures up to 400 degrees centigrade. Thank you for your attention. I'm ready to answer your question.
Thank you, Professor Belov. Alex, do you have any questions? Professor Stolerov. Yes.
Yeah. Thank you for your presentation, Professor Belov. My question concerning the main goal of your investigation. Please explain me what's the role of the electromagnetic process? Why do you need electromagnetic field in comparison with traditional technology, melting?
No, first of all, it's not our technology, it's technology of a Center of Magnetic Hydrodynamic, first of all. But we interesting this technology because this technology provides extra high solidification.
Yeah.
In conventional technology, it's impossible to reach so fast solidification over than 1000 Kelvin per second. But this technology provides such velocity.
Okay, but what is the physical reason for using the electromagnetic field?
Physical reasons, because the electromagnetic fields may because in this case they form a rod, a kind of ingot without crystallizer, graphite or copper. They form aluminum melt in form of rod, for example, with diameter 10 millimeters, and water cool this melt. Direct contact between water, cold water, and aluminum melt. This contact provides fast solidification like in granular technology.
Okay, it seems me clear. Thank you.
Thank you.
Colleagues, more questions? So, thank you for your report, Professor Belov. Now we have time for coffee break till the 20 minutes to 1 p.m. See you soon. Thank you.
No, ma che Franceschi?
Hi, Professor Klaus Dieter. I'm glad to see you.
Hello, yeah, hello. How are you, Alexander Pesin? How are you?
Fine, thank you.
This is a nice conference, yeah.
Yes, thank you. And
I listened to the last talk. So earlier we had a new chancellor at the university inauguration, so I was absent, but now I'm here.
You are in China now.
I'm in China, yes.
Yes.
Yeah.
It's
so
good.
just setting up my presentation.
Now presentation, or maybe it's in several.
Two, 3 talks later, maybe the third after, right?
I will see. I will. I want to be in your presentation.
Oh, thank you. Yeah.
Yes.
Yeah, it will repeat a little bit what I've done last time, what I've presented last year in December, but also I put some bulk metallic glass in, so that's a different story, which I have not talked to this audience yet.
I hope that maybe the situation will become better and you can come here.
Yeah, at some stage that would be great. Yes. I heard from Megumi Kawasaki that she visited maybe 2 years ago.
Yes.
Yeah, and she showed me pictures about steel mills and big industry. And obviously about a great institute.
Yes. I'm sorry.
Yeah, go ahead.
Yeah. Ну, давай браслет. Все, да, спасибо. Все, ничего не надо. Спасибо. Все. Okay. Okay. I have been in the presentation of Megumi, but
yeah, me too.
Yes, but at the end of when it was questions, I should go to rector. They phone and ask me to come, and I have meeting in that time, and I could not refuse. But I listen to your presentation.
Right. Yeah. Actually, Megumi, there was one question from the audience. That's what Megumi said. It's ongoing work, namely the heating stability of these HPT processed materials. In the last few months, we have done neutron and synchrotron studies, and we are now doing the data analysis.
Yes.
So I have some preliminary things, but the very latest things I have not in my talk that just came out. These days I'm working with my students.
Yes, I think.
And with Megumi student.
Yes. We hope to organize the next Magnitogorsk Material Week in October.
Right.
And it will be Magnitogorsk rolling practice in November. Because we try maybe in November the situation will be better and somebody could come offline and we can organize a mixture maybe online, offline. And
we really have to see how that goes with this corona. It's really annoying, also personal for the family. I'm here, yeah, just alone.
Yes, I was ill in December. At the end of December, I was ill, but not so strong, but several
from
days.
Corona?
Yes, I was ill.
Oh.
Yes.
Oh. Yes. I hope it will be good. No long term.
But it's not so It's really strong, but several days, maybe 3 days. It's strong. It was strong.
Wow.
Then it's okay.
You have been in hospital?
No, at home. But 2 days it was a high temperature, but then it's
Good on you.
not usual illness. It's something change.
Yeah. I think that this thing is serious.
Yes.
Pandemic.
We should start. Nice
Okay.
to see you.
I be quiet.
We have our colleague from Spain, from Universidad Politécnica de Valencia. Professor, are you here? So please switch on your microphone and you're welcome.
Yes. Are you hear me?
Yes.
Thank you. So I will compart the screen. Do you see my presentation screen or not yet?
Not yet.
And now?
And yes, you're welcome.
So, thank you. Well, good morning. I will present you the work about the interlaminar fracture toughness of low curing temperature vinyl ester composites exposed to severe service conditions. Realized in collaboration between Polytechnical University of Valencia, Spain, and IMASH in Moscow. First of all, just a moment. First of all, let's see why we are speaking about these materials. Glass fiber vinyl ester composites are increasingly used in the manufacture of equipment and facilities due to their advantages over metals in many engineering sectors, where high temperature or corrosive environment are present. It is useful in many applications and environments. For example, in contact with fumes, in spray heaters of scrubbers, contacting with the hot dust suspensions, in civil infrastructures in fresh water and in contact with seawater, in desalinization plant piping, resisting the brines, and solutions of other salts of hypochlorite, for example. So the typical service conditions are temperature between 30 and 70 centigrades, a variety of solutions as brines, acids, bases, and organics, and the atmospheres as vapor, combustion products, and so on. All these possibilities are due to the outstanding properties of vinyl ester, bisphenol A, VBA, which are high chemical and thermal stability, great strength and toughness. Vinyl ester are stronger than polyester and more resilient than epoxies, and competitive versus epoxy resin because of its lower cost. The flexible nature of the molecular chain produces parts that withstand impacts and repeated flexing without developing cracks. Molding conditions for vinyl ester are similar to those for polyester. So it seems to be useful, to be in use, and to be studied enough. And so what are we speaking about? It is quite typical situation for many materials. They are already in use, but they need the investigation to be continued in order to determine the real limits of their possibilities. In our case, on the one hand, the alterations in curing conditions can lead to VABA composites with unsatisfactory mechanical properties. This is particularly important when in situ manufacturing and repair tasks are carried out on large pieces of equipment, and also when high curing temperatures or post-curing are impossible. On the other hand, composite materials laminates show weakness out of the sheet plane owing to an anisotropic constitution. Interlaminar delamination is the main drawback because of stress concentration in composites and structures and leads to catastrophic material failure. G critical in second mode is enable the quantification of the strength needed to crack propagation in the reinforced sheet plane when interlaminar shear stress are present. This work evaluates interlaminar shear properties, the strength tau, and strength energy release rate, J critical in second mode, of VABA fiberglass composites exposed to elevated temperature in correlation to low curing temperature as an important factor in the manufacturing and in situ repair of engineering equipment. So, what we did, the composite laminates was fabricated using vinyl ester bisphenol A resin by alternately placing e-glass fiber plane fabrics, layers oriented at 0 and 90 degrees and plus and minus 55 degrees up to complete 8 layers. 2 low curing temperatures were used to consolidate the composites, 20 and 50 centigrades, both for 48 hours. Then the samples were cutted, aged at 95 centigrades during 0, 1,200, 2,100, and 5,300 hours. Flexural interlaminar shear stress and mode 2 interlaminar shear fracture characteristics were obtained from specific mechanical tests. The pre-crack of the end-notched flexural fracture samples is an insert of 40 micrometers thick Teflon ribbon. The strain energy release rate G sub-second critical was calculated applying the modified beam theory. Fracture surfaces was analyzed using scanning electron microscopy in order to complement and explain the results of destructive mechanical tests. The effect of different curing temperatures and exposure conditions of VABA composites were investigated by modulated differential scanning calorimetry (MDSC) and by thermogravimetric analysis (TGA). With these efforts, next results were obtained. This table resumes the numerical results of the mechanical tests, calorimetry, and thermogravimetric analysis. Curing temperature plays an important role in composite mechanical characteristics. When the temperature changes from 20 to 50 centigrades, the properties grows by up to 17% for interlaminar shear stress, tau. This improvement is attributed to the increase in cross-linking density. Flexural strengths R, elastic modulus E, and interlaminar shear stress tau show a strong loss regarding exposure time. Losses fluctuate between 16 and 19%. Tau is the mechanical properties most sensitive to high temperature exposition. It falls between 38 and 48 in case of composite cured at 50 centigrades, and increase up to 56 for those cured at 20 centigrades. As occurs with static properties, G, second critical, is very sensitive to high temperatures, and this become more obvious with exposition time. It decreases exponentially with aging time. The differences between the two cured composites achieve 45%, reached 5,300 hours. Interlaminar shear strength tau is the property with the highest degradation degree at around 60%. This means that curing temperature not only influences the resistance to crack propagation, but also the surface fiber matrix adhesive strength. The remaining curing enthalpy indicates that lower curing coupons have greater post-curing capacity, or at least 3 times higher in composite cured at 20 centigrades. Therefore, matrices have different degrees of curing, as indicated by T sub G. It is a glass transition temperature, where high curing temperatures enable higher resin cross-linking. In this case, both T sub G and mechanical properties increase together with improved toughness G in second mode critical. The content of volatile compound registered for TGA results shows that light fractions that volatilize at lower temperatures are related to an incomplete curing process during manufacturing, in accordance with the curing enthalpy obtained in MDSC. No significant differences were found in polymer decomposition temperature. They were 385 and 388 centigrades. The fracture surface shows different morphologic features as a function of curing temperature and thermal composition time. The fracture from the non-aged samples cured at 20 centigrades is clearly defined by the apparition of larger Haeckel formations in the resin-rich area that follow the crack propagation directions along the fibers. The Haeckels are wide, close to each other, and large. That is evidence of non-degraded polymer. For 50 centigrades cured composites, fractures also occur between 0 and 19 fiber yards. The presence of a large number of Haeckel marks means high value of the strain energy release rate, and so improved toughness behavior is obtained. The resin from composite cured at 50 centigrades is seen to be tougher because of roughly closed Haeckels and good adhesion to the fibers. This capacity of the resin to stick to the equilibrated bidirectional reinforcement supports toughness and therefore a high value of G in second mode. The thermal aging effect on the morphology of fracture surface is also identified. After long exposition, the aged samples show a Haeckel packet reduction, sharp facets of Haeckel morphology, and a lack of relief on the surface of these facets. This morphology supports an increase in resin embrittlement as a consequence of thermal degradation. But resin is not only responsible for decreasing the interlaminar fracture toughness. glass VABA interface adherence is also impaired. Composite turns brittle when the resin near the fiber has been thermally degraded. We see that although thermal exposition weakens the composite, this structure morphology reveals that VABA resin retains part of its original toughness and fiber adhesion. Conclusions. The interlaminar shear strength tau and strain energy release rate G sub second mode critical are the mechanical properties more sensitive to the changes in the state of resin and in the adhesion with fiber. So they are the best indicators of the state of composite. Higher curing temperature improves initial mechanical properties because of increased chain cross-linking and the fiber matrix adhesion. The degradability of fiber vinyl ester composite is reverse dependent with curing temperature according to interlaminar shear strength tau and J subcritical. Aging effects are stronger if curing temperature is lower. So using of low curing temperature is sensible. Thanks for your attention, and if somebody has any doubts, I'm supervised.
Thank you for your report. So, colleagues, do you have any question?
I have one question.
You're welcome.
Dear Professor Barinchis, it's nice to see you and hear you, and your presentation, it's interesting for me as well. And my question about some terms that you used, like degradation or degradation and decomposition, and what do you mean?
Sorry, I was occupied with attempt to go out of the presentation, but well, repeat it, please. Sorry.
In your presentation, you mentioned about two terms. First, this is the degradation, and the second is decomposition. What do you mean under these terms?
Not all degradation is due to the decomposition, because during the high temperature attack, because this attack is made in air, the oxidation took place too, and not necessarily the chain rupture must occur, because the composite will lose a part of its toughening phase, which is the styrene phase. It is evaporating. So the loss of properties is due to some transformations inside the composite, not only the decomposition of the components.
Okay, yeah. Thank you. It's clear.
So thank you for your report. We should go to the next speaker from Ufa State Aviation Technical University, Russia. Rashid Asfandiyarov. Rashid, are you here?
Yes. Good day. Are you here? Me?
Yes, yes.
Yes. Okay.
You can share your screen. You're welcome.
Okay. You. You see my presentation?
Yes.
Okay. Good afternoon, dear colleagues. My name is Rashid. I'm from Ufa State Aviation Technical University, and it is our team in this work. This work is devoted to the study of the features of deformation treatment by ECAP and ECAP conform in the manufacture of contact wires for railways lines. This slide introduction. The research is carried out within the framework of a project dedicated to the study of thermal effects during plastic deformation in dispersion hardened copper alloys. Such studies are important for improving modern high-performance deformation processing methods with high heat release, for example, based on continuous conform processes. This is especially true for dispersion hardening copper alloys, since during data mechanical processing, the process temperature and the stress-strain state of the workpiece are the key factors responsible for the formation of the structure, state, and final properties of products. In this slide, you show table of contents of this work. Motivation of our research. Railway transport is one of the areas of application of such copper alloys. And today, there is actually task of the developing high-speed rail transport. An important component of railway line is the contact wire. The appearance of the contact wire in right of slide. The contact wire is a heavily loaded network element even at the normal speeds, which increase significantly when the speed increases above 250 km by hour. Therefore, it is necessary to increase its strain characteristics. However, due to the peculiarities of installation and operation, it is also necessary to preserve the plastic properties of the finished product. Gradient structure in left of the slide are currently attracting the great attention of researchers in the field of material science. It is so that such structures make it possible to simultaneously obtain a high level of strength with the retention of plasticity, with the very important for structural, which is very important for structural materials. So this is how the idea was formulated to improve the complex of mechanical and operational characteristics of contact wires for high-speed railways by forming a gradient type structure. The purpose of the current work to identify the features of thermomechanical treatment, including ECAP conform and post-deformation heat treatment by aging, to ensure the formation of gradient type structure, gradient in grain size in the manufacture of contact wires with a shaped cross-section, and corresponding tasks have been identified, such as study stress-strain state of workpiece during ECAP and ECAP conform, to make a physical experiment to obtain laboratory samples of the contact wire, research structure of laboratory samples, and evaluate the physical and mechanical properties of a laboratory sample of contact wires. The choice of the study material was based on the following advantages of chromium bronze: widespread use, low cost, has high thermal stability, shows a high level physical and mechanical and operational properties. In the ultrafine grain state, it demonstrates a lower coefficient of friction, which is important for the operating conditions of the contact wire. The chemical composition and initial structure state are shown on this slide. Research methods of is computer simulation and experimental ECAP, ECAP-C with the shaping, electron microscope, and tensile test machine. Okay. Computer modeling was carried out for two schemes, ECAP conform on the left of slide with the shaping and ECAP with the shaping on the right of slide. We can see 3D models and the simulations result for the process conforms and piece ECAP. And at the down of slide, you can see matrices for shaping profile of contact wire for both variants. Okay. Previously, with the help of the global complex, we carried out studies of the rheological behavior of the cuprum chrome alloy under conditions of large one-time deformations. Based on the data obtained, the material was set in the form 3D. Boundary conditions and material properties are shown on this slide. So, result of computer modeling. In the course of computer modeling, the main attention was paid to the distribution of accumulated strain and temperature conditions of processing. The figure shows the figure on the top shows the temperature fields during ECAP with the wire shaping in long cross section and longitudinal section. The temperature of in the ECAP zone reaches 490 500 degrees. The temperature in the deformable zone, the temperature during wire shaping in distributed fairly evenly in the 510, 530. The maximum heating is achieved in the pressing zone of the wire and reaches 530. According to the analysis of ECAP conform process of the data obtained, the workpiece in the process is subjected significant deformation heating. So maximum temperature in the central region of the workpiece in the process of forming the wire profile reaches on the bottom of slide. In the peripheral region of the wire profile shaping heating on of the order of 400, 470 is observed. The ECAP deformation zone has gradient distribution of temperature fields from 150 to 300 degrees. The result obtained indicate a high thermal load. These values lie in the range of edging temperatures of this bronze with a positive factor during processing. In this slide, distribution of fields of accumulated strain. The figure shows the figure on the top slide shows that the distribution of degree accumulated strain in the cross section of contact wire. The distribution accumulated strain is fairly uniform. The values of accumulated degree of strain are 2.53. In top. The field of accumulated strain distribution for ECAP C with the shaping are present in down of slide. According to the data obtained, the accumulated degree of deformation is finished. The wire has gradient character and reaches 6 units in the low region. Of the periphery. 5 units in central region and 3 units in the upper region of the periphery. This gradient distribution creates the prerequisites for increasing the operational properties of the finished wire, since the lower region of periphery is low due to the friction during the movement of current collector, and increased accumulated degree strain will contribute to the increase strength and wear resistance. After the simulation, we make a physical experiment to obtain laboratory samples by ECAP method with the shaping. The initial temperature of the tooling and the sample during the deformation was 450 degrees. Deformation rate 10 millimeters by second. The workpiece diameter is 20 millimeter, and the length is 100 millimeter. In the course of the research, thermometry was also carried out. In the bottom of slide, thermometry was carried out using a tester thermal imager. The result of which are shown on this slide. It was found that maximum heating temperature of the sample at the exit from deforming block is 490 degree, which correlates with the values obtained during simulation. The end result of experiment. This slide shows an image of obtained laboratory sample. On the top of slide, structure studies have shown that after deformation and edging, a strip-type structure is formed. The average size of bends at the mesoscale is 20-25 microns. Picture in left of the slide. Large chromium particles are observed located mainly along the boundaries of the bends. The average particle size is 1.5 microns. Analysis of the misorientation map is the analysis of the cuprum chrome alloy after the final ECAP treatment with the molding, molding and subsequent edging at 450 degrees for 1 hour indicates the formation of strip-type structure with the high angle boundaries, and accumulations of recrystallizing grains are observed along the boundaries of these bands. The size of recrystallization grains are on the order of 3 microns. Due to strong local heating under conditions of shear deformation and general evaluate temperature conditions are created for the recrystallization process, which occurs along the high angle boundaries of the bands, with the turn leads to microstructural heterogeneity with the can characteristics a gradient 1. The next investigation of physical and mechanical properties. Studies of physical and mechanical properties have shown that after ECAP, with the shaping, the ultimate is 470 MPa. Left graph. Additional precipitation hardening after edging makes it possible to increase the value of the ultimate stretch to 540 MPa, and in the slide right graphs, the relative elongation of the laboratory sample of contact wires has a relative elongation with the 19%, most likely due to the strip structure and the formation recrystallized fine grains along boundaries of the strips. The restoration of electrical conductivity to 69% of AX during deformation by ECAP with the shaping is explained by the high deformation temperature and higher local heating up to the 520 degrees is deformation zone. As at this temperature, the diffusion activity of chromium increase in difficulty, and the process of deformation simulated decomposition of the solid solution is more activity than room temperature. An increase in electrical conductivity to 75% after aging indicates that not all the solid solution decomposes during deformation, but most of it. The next experiment, ECAP conform with the wire shaping. A physical experiment was carried to manufacture a laboratory sample of contact wire using ECAP C with the model material, technically pure copper. In the course of the experiment, long laboratory samples on the bottom of slide. In the course of the experiment, the linear velocity of the material flows was 16 mm by second. Initial billet temperature 350 degrees. The structural state is shown on this slide on the center. It can be seen that in the peripheral regions there is a more efficient refinement on the structure than in the center, which is associated with the deformed building equipment. These results show that the possibility of applying the ECAP conform method with the shaping in the manufactured contact wires. On this photo, longitude sample of laboratory samples. Sorry. And summary. As a result of the study, the following main conclusions can be drawn. By the method of fine element computer modeling, the temperature parameters and deformed state of the workpiece in the process of ECAP with the shaping and ECAP conform with the shaping. It was noting the significant impact of processing speed. Verification of computer modeling of the ECAP shaping processes by method of physical experiment showed that deformation by ECAP method with the wire shaping at the 450 degrees and speed of 10 millimeters by second, subsequent agent provides a strip type structure. The average size of bands 20-25 microns, large chromium particles is observed, located mainly along the borders of the bands. ECAP with the shaping and subsequent engine provides high physical and mechanical characteristics of laboratory wire samples from cuprum chrome alloy, ultimate tensile stress about 540 MPa, plasticity about 19%, and electrical conductivity 75 MPa. And thank you for your attention. Invite for cooperation. Okay.
Thank you for your report, colleagues. Do you have any questions?
May I ask a question?
Of course.
Please, can you explain the reason for increase in electrical conductivity after ECAP in comparison with the initial state?
Okay.
Yeah.
Okay.
Strange.
In the process of head treatment, after 1 second, please. How to say? Распад.
Dissolution.
Dissolution of
solid.
Да, sorry. Dissolution of solid particles and special hardening.
Thank you.
Daria?
Yeah, just a couple of questions. On this slide, tensile tests were performed at which rate and which size of samples you used?
we can use, or we use the standard we use the mass sample of wire, not standard sample. We used this sample.
Okay, and at which rate?
Rate is 1 millimeter by minute.
Okay. And another question, maybe you mentioned it, but I could miss it. How long the road built by ECAP?
This is a continuously process, and in this photo on the bottom of slide, 1 meter 17 centimeters, and theoretically and practically we have not a limit of length of sample.
Okay. And one very stupid question, especially simulation. You mentioned two programs at the beginning, I mean, Compass and Deform. Am I right? You use Compass to build equipment and Deform to provide experiment?
Yes, in the Compass, we, how to say, in the Compass, we prepare 3D models of equipment, and in the form we make simulation.
Okay, thank you for your presentation and for your answers.
And one more question about simulation. During this process, you have rather severe stress strain state and changes of size during this treatment. But did you use some remeshing rules in your simulation?
The size of elements we found from the size of sample.
Because during simulation of such processes, you can receive a little bit different strain distribution in simulation with remeshing rules and without remeshing rules. This is just for discussion. You can check it. Maybe it will increase your prediction by computer simulation.
Okay.
Okay, thank you. We should go to the next report. Thank you. From Professor Liz from Israel Institute of Technology, China. Professor Liz, are you here?
Sorry, I have to put the microphone on. I try to share my screen again.
Yes, yes.
Can you see the screen now, right?
Yes, yes.
Okay, yeah, thank you so much for the introduction and the opportunity to give this presentation in this very honorable symposium and materials week. I will talk about materials at high temperature probed by in situ synchrotron and neutron radiation. And maybe I need to get rid of that little thing here, which covers my screen. So I'm from the Guangdong Technion Israel Institute of Technology. We are in an outstation campus from the Technion in Israel, in China. This symposium is in memory of Alexander ZHILYAEV, and I had the pleasure to know him about 2-3 years ago, where we met from then on TMS conferences, and also personally came well into contact. And he had the idea and the approach to do X-ray diffraction, and we discussed quite a little bit and became very friendly towards each other. And at the end, I will run out of time in my talk here in this presentation. So I give some last words which I have had with Alex, given here about 1 year ago. You see, this is in March last year, and then others, yesterday, 1 year ago, where I have been Corona lockdown together with Megumi Kawasaki in Oregon, and I sent him a text about Oregon, and hi Klaus, how you gonna stay in Oregon till summer? Alex was right. I was staying there until summer. At that time when we messaged, I did not know yet how long I would stay there. And there's a good news, he said. We have got funding for you and Megumi to visit Russia and Magnitogorsk. Unfortunately, we know that that did not happen in his lifetime, so this is sad, but I have very good memories to him. I give the same lecture again on hoop stresses, and we had a good demonstration on the hoop here on this barrel. And he asked me, is this antivirus medicine? The color of wine is different. So he was thinking ahead already to the antivirus medicine. And then he commented, Alex commented about the cost of the barrel and several months to drink it. Would love to drink with him together, but yeah. So the overview of my presentation is I give motivation to in situ studies, then a brief examples on a few metal systems. Maybe I give only a short presentation on aluminite, titanium aluminite, and include some bulk metallic glasses, and then severe plastic deformed material by high pressure torsion. The project I started using neutron and synchrotron diffraction methods for the investigation of thermomechanical processes to exploit novel methods using both kinds of radiation, and also looking deeper into data analysis to get more out of the data than conventionally done. And points are the multidimensionality. So look to it with a two-dimensional detector, look to it time resolved in situ. And of course, we want to bridge the scales from the atomic to the engineering structures and anything which is in between, merging the disciplines between instrumentation of neutron and synchrotron radiation, material science, and of course the physics and the engineering part. And I did not do everything myself alone. I had collaborations. So in the past years, some of the most important are here at Oregon State University, which I mentioned, University of Wollongong, Australia, the Japan Atomic Energy Agency, and the Montana University of Leoben. And starting with Alex, and hope to continue with you guys. I'm very confident, and we have some samples already. The idea is to measure in situ the structure while processing a material with neutrons or with X-rays. Conventional characterization is done. You process the sample, you quench it, cut it, and then you look to the cut surface, either with microscope, optical light, electron microscopy, or even not so deep penetrating X-rays, and start over and over again with other different processing parameters. So different temperature, different holding time, and everything you can imagine. Of course, the advantage of neutron and X-ray in situ diffraction is that we get information during the heating or during a plastic deformation in real time and time dependence. Do we want to use neutron or synchrotron radiation? Well, I have not much time, but they give different contrasts, the neutrons to the X-rays. They are also highly penetrating, so you can have good grain statistics if you're working on coarse grain materials. So that's probably not so much for the nano grain community, which is effective for quantitative phase analysis and texture analysis. It has a magnetic moment. You can see hydrogen and other nice things. And the synchrotron X-rays, they are small, they're brilliant. You can get statistics from very small volumes, such as single grains, even sub-micrometer grains. You can have time resolution, and you can have a high reciprocal space resolution. So the peak shapes and everything, what you see, the distribution in orientation space. This is an example from steel making, which has a casting problem. But I just want to demonstrate, if we go to very high temperature, as shown here in the red part of the figure, then we see here the austenite phase at high temperature. There's grain growth, and we go to very high temperature, maybe even higher, 1722 Kelvin. We go to the delta ferrite phase in low carbon steel. And as we cool now, in a few seconds, you will see that there's a distortion of the crystal lattice. When we go, now it's the cooling process, and here's the distortion of the crystal lattice during the phase transformation. So we get the new phase, but also we get the distortion, and we can work out the distortion due to the phase transformation. That is the interest. Just a short example here. Synchrotron radiation studies are very simple. So we have a fine incoming beam, and in the far field we have a two-dimensional by diffraction rings, concentric rings in this case, shown here on titanium 45 aluminum 10 niobium. And this was before some heating process where we have a very fine-grained material, and after the heating cycle, and we would get all the information in between during the heating as well, like shown in the steel example, what is happening. Of course, going from here to here, we have grain growth, we have accumulation of intensity here. There's already accumulation of intensity, so there's already some texture in the starting material, which then may emphasize into larger crystal grain orientations after grain growth. Not too much time to go there. When we do plastic deformation, we can look now to the azimuthal angle as a function of time. So we reproduce the intensity along the azimuthal angle as a function of time and get these azimuthal angle time plots. So the angle is on the X scale, the time is on the Y scale. For various reflections, you can do that for each reflection ring and get these streaks, these streak camera images. And as we start plastic deformation, before we have some sluggish grain growth while we heat up, but then and some recovery, but then as we are at high temperature, as you can see here to the right, as the temperature, we start plastic deformation, the green curve, and see how the grains reorient. They may reorient with a shift to the left, with a shift to the right. This is grain rotation due to the slip, but we also see the distribution within this this cone of breaking into subgrains, and the spots, the dots in there due to dynamic recovery. These are temporal fluctuations, so the time scale is here vertical. They occur only, these orientations, they may, in the beta phase, only occur in short moments of time due to a high rate of dynamic recovery, competing the grain breaking process and the grain annealing process. And we can work that out in titanium aluminide. That would be the the beta phase would take the high plastic deformation load, while the alpha phase deforms sluggish, and the crystals, so to say, they swim in the beta phase. So the beta phase is the grease of the plastic deformation process. We could do more with neutrons. I just want to point out, if we have conventional X-rays, we may have peaks at these positions, very high peaks. With neutrons, we see these peaks here at those positions, which are the superstructure reflections. And the superstructure reflections, they are sensitive, very sensitive to the order and the disorder of the material. And this is because titanium has a very different contrast with a minus negative scattering length. But now time to go there, because I like to talk a little bit about more into nanostructured material. So this is quaternary bulk metallic glass, which I like to present here. A mixture, these are the compositions, so zirconium-based, copper, nickel, aluminum, and mixtures of binary deep alloys, and they have a high glass forming ability, as shown here by the group of Professor Xun Zhen here in China. And he also made the specimens for those studies. So the material is fully amorph, and in selected area diffraction, you also get amorphous, typical amorphous diffraction patterns. Then with X-rays, this is now synchrotron X-rays, we can calculate from the diffractograms the pair distribution function and see that we have a near range order where we see the change of the bond lengths as we change the composition of the material. And as we go far out here in this range, we see coordination spheres. However, what I want to show you now is in situ heating and compression studies of this bulk metallic glass. So two independent experiments. The one is compression at room temperature and the other is heating. So what happens if we compress the material? Then we get elastic strain, and the elastic strain leads to a strain ellipsoid. So in the longitudinal direction, the Debye-Scherrer rings, it's 1 over the lattice spacing. So the Debye-Scherrer rings become larger in the longitudinal direction, and with Poisson's ratio, they shrink in the transverse direction. And as we plot now the radius of these diffraction maxima as a function of sine square psi, the orientation angle when you go around the ellipse from the longitudinal to the transverse direction. So it's a lattice strain or the atomic strain. It's not really a lattice in amorphous material. Then we can fit a straight line to each color family here. Each color family is a different compression step, what we have done. And this is the strain ellipsoid as we go along one ring. And from that, we can calculate Poisson's ratio. So we can calculate the lattice strain. The lattice strain in the compression direction goes down, and Poisson's ratio is going up, and it goes up to 0.5. So this is really volume conservation. I put this on this slide. So we have in bulk metallic glass the macroscopic strain and engineering stress curve, and also the atomic strain curve here in red. With atomic strain, we only see the elastic part, we don't see the plastic part after yielding. But then looking into the atomic strain versus the total strain, we get in the longitudinal direction some saturation, some yielding, while in the transverse direction, we still get increase of strain. The atoms dilating further. And Poisson's ratio then, upon yielding, increases. Now, so we have a certain strain about 15 times 10 to minus 3, where the material starts to flow. Now let's do atomic expansion upon heating experiment, where we can look to the thermal expansion, so the lattice strain or the thermal strain as a function of temperature. And we can do that for the first peak here in our scattering function, in the measured signal. Then we can do it for the second peak, for that peak as well. And we get a different slope. We get a different thermal expansion. We also can calculate the pair distribution function and then plot the first nearest neighbor position and the second nearest neighbor position. So the first nearest neighbor, they have a minimum slope, and the second nearest neighbor, they have a much stronger slope. So what is happening? In bulk metallic glasses, you may find these building blocks, icosahedral building blocks, but you have the nearest neighbors and we have the second nearest neighbors across here. And what's happening, what the observation is, the nearest neighbors, they somehow expand, but the second nearest neighbors, they expand much faster from the first, from the zero atom. Meaning we get a shear stress, we get a shear strain. And of course, if you put now building blocks together in different orientations in the vicinity of each other by the continuity of the matrix, we get shear stresses. Now let's put one and one together. So for the metallic glass, we get a yielding about 14 times 10 to minus 3. And we get here a shear strain in the thermal expansion about 8 times 10 to minus 3. This is the same order of magnitude for both of the materials. And therefore, we conclude that the glass transition is the point where the shear of these building blocks yields. So we can put glass transition and shear yielding strength together on one scale. I think I'm running out of time. Maybe in just 1 minute or so, I resume or I fly over it, what we do with our dear Megumi Kawasaki, who gave a plenary presentation here. And you have seen the high pressure torsion results of her. What we do, we go together with Megumi and her student, myself, my student is involved, to the J-Park facility in Japan and do heating experiments during while capturing neutron radiation. And now I'm a little bit puzzled because my screen does not continue. Anyway, I think I'm running out of time. Yeah, I can scribble here. So what we see, basically, we get a peak width, we measure peak width with neutrons, and as we are near, this peak width shrinks. And the shrinking, if we plot now, the shrinking or the peak width versus the temperature, we get sharp transition temperatures. And these sharp transition temperatures, they indicate the recrystallization temperature. We also can do Williamson-Hall plots and get measures of the strain, of stress-related strains, so residual stresses between the microstructure building blocks, which relax before the recrystallization temperature. So we can observe and get recipes how to make ideal microstructures where the deteriorative stresses relax before recrystallization sets on. I'm sorry that my screen is blocked, but I think my time is over anyway. So I just wanted to give a brief introduction into in situ neutron and synchrotron studies. And at the moment, we are doing a lot on high pressure torsion materials together with the group of Megumi Kawasaki and with samples which even have been prepared by Alex ZHILYAEV. With this, I really would like to thank you.
Thank you for your inspiring report. Some pictures look like modern art. Future is coming, I think. Colleagues, do you have any question? I have. We don't have time, but I have to ask one question, a few questions. What about materials limitations for such research method? Is it possible to observe deformation of all materials from steels to copper,
yes,
for example?
so the penetration of neutrons, there are very few materials which are not transparent for neutrons, absorbing boron, for example. Titanium has a negative scattering length, so some of the titanium alloys, they don't give a good scattering signal, but otherwise you have with neutrons a very good penetration, centimeters or tens of centimeters into material. With high energy X-rays of 100 keV, you also can get millimeters to a centimeter into the material, and that opens possibilities to a large variety of materials, to metals, ceramics. Even if you have lead, easily we get through 3 millimeter of lead, PB.
Okay.
So it's really a bulk study. If you do surface science, there are other methods, but that's maybe out of the scope of this lecture, but there are also methods.
So I think this is so good presentation, and we have such lack of time, but maybe you continue your presentation at our Magnitogorsk rolling practice in the end of this year.
Thank you. Yes, I mean, I'm still looking forward to coming one day. And Alexander Pezin, he also expressed this invitation. We will see how it goes with Corona. Yeah, thank you so much.
Yes, I will make some presentation about this event, and you can understand when, where, how, and so on. So,
yes.
So thank you.
And there will be soon some work coming out with Magnitogorsk samples. Yeah.
Kawasaki, we are waiting for you.
So we have to go to the next report from Denis Aksionov for Institute of Molecular and Crystal Physics, Russia. Denis, are you here?
Yes, I am here.
Sorry for delay. You can share your screen.
Okay. Do you see?
We see your presentation. You're welcome.
Okay. Good afternoon, dear colleagues. Theme of my report is deformation gradient and structural features during free bending of copper materials. Despite the fact the SPD methods allow one to obtain unique properties, these methods are still limited in their application. For example, the method of ICAP conforms has tribological difficulties. During its implementation, there is a high heating of the material and high stresses. In this presented work, as an alternative method that improves manufacturability when hardening long asymmetric workpiece, with a slight change in the cross section, A method of alternating plastic processing by bending the workpiece around the roller is proposed. It is known that with alternative bending, active hardening takes place up to the appearance of a fracture. This effect of bending hardening was taken as the basis for developing the method. As a rule, gradient structural states show increased values of strength and ductility. Obviously, during bending, a strain distribution gradient is observed, which leads to a gradient refinement of the structure and a gradient hardening of bulk workpieces. In particular, the research is devoted to the study of the deformation gradient during static and dynamic bending. We used two materials. This is oxygen-free copper and copper chromium alloy with contain copper chromium, 0.5% weight percent. For both states, heat treatment was carried out in order to relieve residual stresses. Thus, a coarse-grained state with an average grain size of 40 microns is formed in copper, micro-hardness 600 megapascal, and tensile strength 210 megapascal. Coarse-grained state of copper chromium alloy was also formed in the alloy. The average grain size is 120 microns. Micro-hardness, which was 600.5 megapascal, ultimate strength 220 to 150 megapascal. Static bending of oxygen-free copper and copper chromium alloy was carried out according to the following schemes. Scheme A assumes bending in only one direction. Pattern B is bending is one direction and then rotated to 19 degrees of the specimen after each bending cycle. And scheme C assumes bending in two mutually opposite directions. Analysis of the obtained patterns of the strain state reveals that in the process of bending, irrespective of the road and number of processing cycles, the accumulated strain distribution in the sample has a non-homogeneous character, with the larger values in the peripheral regions of the billet and smaller values in the center. The diagrams of accumulated strain distribution have a non-symmetrical parabolic view, which indicates a gradient strain distribution in the section. The non-symmetrical strain distribution shows that at the initially outer radius of bending, the region of compression after straightening, much higher strain values are accumulated than at the interior radius of bending, the region of tension after straightening. One processing cycle leads to producing approximately the same accumulated strain in both the copper samples. Further deformation by bending promotes strain accumulation. Road C produced a more homogeneous and symmetrical state than road A. You can see in this. However, road A leads to a proportional growth in accumulated strain. Unlike road C, where the growth of accumulated strain after the first processing cycle declines considerably, and after 4 cycles, the maximum values reach only 1.2, 1.4. Instead, the expected 1.8 or 2. In the initial state, oxygen-free copper is characterized by a coarse grain structure with a mean grain size of 40 microns. Multiple growth twins are observed in grain interiors. After one cycle of processing by bending, a surface deformed layer with a thickness of 20-40 microns is formed. The layer structure represents elongated cell with a mean size of 1 microns and the elongation factor 1/2. In the rest of the volume, a coarse grain structure with a grain size of 35 microns is observed. An increase in the number of bending cycles to 4 does not lead to an increase in the thickness of the deformed layer, and the grain size in the central region on the sample is preserved as 34 microns, irrespective of the road. Growth twins are preserved in the grain interiors. The macroelectric hardness values across the section of copper processes by bending indicated a gradient strain distribution. The minimum microhardness values are found in the central region. The microhardness in the peripheral region subjected to tensile stresses is 1.2 times lower than microhardness value in the compression region. In both oxygen-free copper, in copper, considerable strengthening takes place already after one bending cycle. The maximum microhardness values are reached after 4 cycles and amount to 1090 megapascal. According to the result of mathematical modeling for static bending of copper chrome alloy, the pictures of the deformed state of the copper alloy after 1 and 8 bending cycles at room temperature were obtained. Analysis of the obtained picture of the deformed states shows that after one cycle of processing, the copper alloy accumulates approximately the same deformation, and its similar distribution is observed in the longitudinal section of the sample. The result obtained indicates that the deformed state is responsible for the geometrical parameters of the workpiece and the roller relative to which there is a bend. The asymmetric nature of the deformation distribution indicates that in the course of one bending cycle, the outer region of the workpiece that has passed the tension compression cycle accumulates high deformation values, and their maximum values are almost 40% higher than in the area that has passed the compression tension cycle. In this regard, it is apparently advisable to change the direction of bending to the opposite to obtain a more symmetrical deformed state. Further deformation by bending contributes to the accumulation of deformation. The result obtained indicates that the deformed state of the samples becomes more uniform with an increase in the level of accumulated strain. However, as a result, we do not observe an additive addition of the accumulated deformation obtained after the first processing cycle. The obtained values of the accumulated deformation after 8 cycles are rather high values in the range 2.1 to 2.2. The difference between the maximum and minimum values decreases markedly with an increase in the number of bending cycles. After one cycle of deformation by free bending along route A, the transformation of the original structure is noted. So in the sphere area, subject to maximum deformation strength, stretching, compression, the structure is refined, especially intense in the surface layer 10, 15 microns thick, where elongated grains with an average transverse grain size of 4 microns are observed. In the opposite surface region, subject to maximum compression tension deformation, there is also intensive refinement of the structure in the surface layer 10, 15 microns thick, where elongated grains with an average transverse grain size of 4.5 microns are observed. Slip bands are visible in the body of some grains. These, for example, perpendicular to the action of the main tensile stresses. The central region is little subject to change, while large grains with initial growth, twins, and undeformed boundaries are observed. An increase in the number of bands to 8 leads to further transformation of the structure, while a highly crushed safe layer 10, 12 microns thickness also continues to form, and the central region of the sample remains coarse. Elongated grains with an average size of 4.2 microns are observed in the peripheral layer of the outer face. In the peripheral region of the inner face, only a crushed deformed layers is observed, and closer to the center, large initial grains. In the central region, a coarse grain structure with an average grain size of 40-45 microns is preserved. The results of measuring the microhardness reflect the structural change of the material under study in the process of the deformation processing by bending. In the copper chromium alloy, the peripheral layers are hardened more intensively, and after one cycle of deformation have a hardness almost 1.5 times higher than the central region. After 8 cycles, regardless of the road, this hardening tendency persists. To implement the scheme of dynamic bending of a long workpiece, a special installation with a forced rotating roll was used, along which the bending takes place, while the speed of the actual displacement of the samples was adjusted using a drawing stand. Slide shows the patterns of the stress and strain states in the conditions of stationary and dynamic bending of the billets. Analysis of the patterns reveals that during the continuous bending of a rod, alternating strain is observed around the rotating roller, unlike in stationary bending, as indicated by the alternating interchange of compressive and tensile stresses. At the outer radius of the middle of the bend angle, the positive values of the average stresses tension, and then negative values compression, whereas at the interior radius the picture is reverse, compression tension. As a consequence, unlike in static bending where only tensile stresses are active at the sample outer radius and only compressive stresses are active at the sample interior radius. In the continuous bending of the sample, alternating extremely non-monotonic strain is observed. The accumulated strain level is also influenced by the bend angle. It was found that with increase in bend angle and number of processing cycles, the level of accumulated strain and its absolute values in one processing cycle grow, which is quite consistent. For instance, for the bend angle of 60 degrees, the maximum accumulated strain is 2.7, and for 140 degrees, 5.8. However, this value is not directly consistent with the bend angle since a triple increase in accumulated strain is not observed. Analysis of the stress state shows that the average stresses particularly do not depend on the bend angle. With increasing number of bending cycles and correspondingly strengthening, the maximum level of average stresses increases and can reach critical values. Considering this fact, virtual studies can be used as a method of control and compression with permissible stresses during the bending of metallic samples, depending on the grade of the material and study. In addition, this type of analysis is useful for designing a processing chain where the permissible stresses are ensured by means of varying the processing parameters in the conditions of multi-cycle processing and fabrication of defect-free billets. For instance, for the first cycle, when the ductility reserve is maximum, it is most logical to use large bend angle. Structural studies show that after 4 cycle processing, a graduate type structure is formed in the cross-section of the billet, and the peripheral layers of the sample are refined more intensely than the central region. And the studies show that after the bending, the cross-section area of the samples slightly decrease, but even after 4 processing cycles, the reduction does exceed 10%. The micro-hardness is distributed non-uniformly. In the longitudinal section, the maximum strengthening is observed in the peripheral layers of deformed billets, and the minimum strengthening is observed in the central region. The main increment in strength occurs already after the first processing cycle, the overall strength of the rod after the multi-cycle processing by free bending for 4 cycles increased for 260 to 375 megapascal.
Andrei,
Okay, I finished now. A show about a gradient strain distribution is observed during alternating bending, which leads to a gradient structure refinement and gradient strengthening of bulk billets. Normally, gradient structural states demonstrate increased values of strength and ductility. In this connection, the method of multi-cycle alternating bending of billets around a roller provides certain performance advantages of contact wire, forming a finer structure and variably increasing the strength, and the peripheral layers of a wire increases its wear resistance in the processes of operation. And I think I can finish these conclusions. Thank you for attention.
Thank you for your report. Colleagues, do you have actually one question? Because we ran out. So I have one question about surface quality of your final product. Do you have some requirements for such product in industrial scale, and is it enough is it enough for your process to obtain adequate quality of micro relief, quality of your surface of your samples?
We think that method of bending we can use in, for example, these schemes for prepare structure, gradient structure, and then then we can additional deformed any another methods.
Okay, thank you. So we have to go to the next report from Andrei Belikov, Belgorod State University, Russia. Andrei, are you here?
Yes, I'm here. Do you hear me?
Yes, yes.
Okay, can you see? So, shall I show my screen? May I start?
We don't see your screen.
How about now?
Yes, you're welcome.
Yeah, thank you. Good afternoon, ladies and gentlemen. Today, I would like to present our current results. Sorry. No, stop. Wrong presentation. once again, I'm very sorry I missed the presentation. So now it is correct presentation with our current results on impact toughness of high strength steel with nanocrystalline lamellar type microstructure. Carbon steels and high strength low alloy steels are most frequently used materials in building structures and machinery company, and among a number of advantages of these steels, they have one major drawback, which is associated with relatively high temperature of brittle to ductile transition, which is associated with the difference with the brittle fracture stress and yield stress, which increases with an decrease in the temperature, leading to brittle fracture at temperatures right below zero temperature. To increase the impact toughness of steels, they should possess or larger brittle fracture stress or decrease the yield stress, which may lead to decrease in the temperature of brittle to ductile transition. To resolve this problem, about 60 years ago, several processing methods, thermomechanical processing, known as ausforming, which involves the plastic deformation of metastable austenite just before the transformation, or modified ausforming, starting with deformation in stable austenite, then goes to metastable austenite at temperatures below recrystallization to obtain the deformation austenite, and then transformed martensite from deformed austenite, which can increase the impact toughness, especially at toughness, especially at low temperatures, along with the remarkable increase in the yield stress and tensile strength of steels. Recently, an interesting approach has been proposed by a group of Japanese researchers, Kimura, Tsuzaki, and authors from the National Institute for Material Science. They made a warm rolling at temperature of tempering. So the medium carbon steel has been quenched to martensite, then tempered, and then subjected to bar rolling to a rather large strain. In this case, it's about 1.7 true strain. And then they obtained quite interesting results. The samples didn't break away and experienced delamination along the specimen. And the interesting phenomena is an increase in the impact energy or impact toughness with a decrease in the test temperature. Quite unusual behavior for carbon steel and high strength steels. The impact toughness increased as temperature decreased. To clarify the effect of TEM forming, they called this process as TEM forming, and then several research groups from China, Japan, and our group also joined to investigation of this interesting phenomena. I mean, terraforming, which may lead to delamination toughness. To clarify the effect of tempering temperature or temperature of terraforming, we selected low carbon, high strength steel, which has been rapidly cooled from 1100 degrees C, followed by tempering at 3 selected temperatures from 600 to 700 degrees C for 1 hour, and then processed by plate rolling to total strain of 1.5. Rolling reduction was about 10% per each pass, and the samples were reheated to rolling temperature repeatedly after each rolling pass. This is the deformation microstructures developed by terraforming at different temperatures. Large strain rolling resulted in development of highly elongated grains in the along the rolling direction, with the transverse grain size well below 1 micron, depending on deformation temperature. The transverse grain size is about 350 nanometers to 950 nanometers. Warm rolling resulted in typical texture developed during plate rolling of BCC materials, namely strong alpha fiber texture, gamma fiber. Intensity of gamma fiber increases with increasing rolling temperature, and eta fiber also intensity of eta fiber increases with increasing temperature of terraforming. Fiber texture were developed simultaneously with two texture components: rotated cube, especially clearly seen at relatively low rolling temperature, and so-called E component texture. Here we can see the large texture associated with E component. The deformation substructures consist in highly elongated subgrains with a mixture of medium, say, small to large misorientations, and uniform distribution of dispersed carbides. Here, carbide particles are mainly represented by chromium-23 carbon-6 oxides, carbides, sorry. And the transverse subgrain size is about 90 to 190 nanometers, depending on processing temperature. Also, the deformation substructures involves rather high dislocation density, well above 10 in 14 meters in -2. Depending on the terraforming temperature, the yield stress increases remarkably from 700 megapascal at the highest terraforming temperature of 700 degrees C to above 1200 megapascal at the lowest temperature of terraforming of 600 degrees C. This remarkable strengthening was associated with the development of ultrafine grain microstructure with large fraction of high angle grain boundaries and high dislocation densities. The grain size can be represented by a function of carbide particle dispersion, similar to well-known Zener pressure, Zener pinion pressure by of grain boundaries by dispersed particles. And the dislocation density can be related to subgrain size. This is transverse subgrain size, leading to say Taylor type relationship. And then the main contribution to the strength of materials can be associated with grain size and dislocation density at after them forming at 6 and 650 degrees C, and mainly grain size or grain refinement at in the samples subjected to them forming at 700 degrees C. Steels after them forming exhibited high impact toughness. These are excuse me, impact scars obtained by impact tests at different temperatures down to liquid nitrogen temperature. The cars obtained in samples then formed at 6 and 650 degrees C shows a similar shape with general yield followed by strengthening to maximum, then gradual decrease in the impact load followed by rapid drop associated with the fracture arrest followed by gradual decrease in the load. And the samples processed at the highest temperature of 700 degrees C showed rapid fracture right upon maximal load, then crack arrest followed by gradual decrease in the load until the end of test. And similar to original results of Kimura and co-authors, the low carbon high strength steels also shows an increase in the impact toughness with a decrease in temperature after them forming. These are typical fracture surfaces of our samples. It's clearly seen here that fracture along the specimen, this surface is characterized by mostly brittle fracture, whereas the fracture crosswise to the specimen, this portion of sample or these small steps and cracks crosswise to the samples or along the impact direction are characterized by a kind of ductile fracture with deep dimples on the fracture surface. To explain the unusual behavior, namely increase in the impact toughness with a decrease in the test temperature, Japanese colleagues proposed an interesting schematic drawing. They modified Yoffie diagram as shown here. The cleavage stress along the transverse direction is characterized by the minimal value, whereas the cleavage stress along the rolling direction has the maximum, irrespective of test temperature. On the other hand, the yield stress, in spite of similar tendency in respect to direction of specimens, they have a strong temperature dependence. Namely, the yield stress rapidly increases with a decrease in temperature. This leads to an interesting behavior. Decrease in temperature below here T1, the first region of this schematic drawing, is characterized by the cleavage stress along the transverse direction smaller than the yield stress of general yield. This leads to delamination, and gradually increasing yield stress results in increase in the impact toughness until the cleavage stress at some angle or crosswise to specimens along the rolling direction will be smaller than the general yield, then leading to rapid decrease or drop in the impact toughness, leading to almost fully brittle fracture. Finally, I would like to conclude, summarize our results. That informing at 600 to 700 degrees C led to development of lamellar type microstructure composed of highly elongated grains and subgrains with a transfer size well below 1 micron and the high dislocation density above 10 in 14 meters in -2. This microstructure provides a remarkable strength, and the yield strength comprises almost 700 megapascal or 1200 megapascal, depending on processing temperature. Temformin at 600 to 700 degrees C increases the impact toughness remarkably, which is well above 100 joule within the all studied temperature range. The maximal impact toughness could be obtained after temforming at intermediate temperature of 650 degrees C. The high impact toughness is associated with high maximal loads and loads at general yield during the impact test. And also, following the strain hardening at an early stage of impact loading, the fracture behavior of temformed samples involved rapid delamination crosswise to impact direction, which also increases the impact toughness. Thank you for your attention.
Thank you for your report, colleagues. Actually, one question. Do you have some questions?
Just a second. Right. Okay. Just I do understand in general why we have to use this experiment. Could you please remind me why you use temperature 600 and you use the big, how to put it? Just
rate. Temperature rate.
Yeah.
You mean the temforming temperature?
Yeah, why do you choose 600, 650, 100, and 700 degrees?
This is a typical temperature range, maybe except of 700 degrees C. 6 and 650 is a tempering temperature for high strength steels. After quenching to martensite, the tempering temperature is commonly selected as about 6 to 650 degrees C to obtain the best combination of strength and ductility. We also include a large higher temperature of 700 degrees C to cover the as large temperature interval as possible.
Okay, thank you. And you perform these experiments only on steel? I mean, on this type of steel, or maybe use some different marks?
Yes, we use the steel because actually this temp forming was aimed to increase the impact toughness of carbon steels, which have a main disadvantage is a relatively high temperature of ductile brittle transition, which limits the application at temperatures just below zero, at negative temperature. So these carbon steels or high strength steels cannot be used safely in various constructions.
So
and to solve this problem, we propose the temp forming.
So thank you for your report. We should go to the next report from our friends from University of Padua, Italy, Mattia Franceschi. Are you here?
Yes, I'm here. Do you hear me, Dimitri?
Yes, everything is okay.
Okay, now I will share my screen. Okay. Did you see the presentation?
And yes, you're welcome.
Okay. Good morning to everybody. It's a very big honor for me to attend this conference in memory of Professor ZHILYAEV that I met for the first time during the first edition of the Materials Week during my master thesis that I did in Magnitogorsk. I really appreciate him as professor and also as man, especially for his tendency to promote the sharing of knowledge between students from different countries. And I really appreciate that experience with him. Today, my speech will be about the development of a novel composition of high silicon carbide-free nanostructural steel, assisted by trip effect. Trip steels are still characterized by the Martin-Sitting transformation of retained austenite embedded in the microstructure. These steel were discovered from the 60s, and the first application started in the 80s by some steel makers company. The microstructure of the first generation of triple-assisted steel was mainly characterized by allotropomorphic ferrite, bainite, portion of martensite, and of course retained austenite. The later generation of this kind of steel are characterized by a carbide-free microstructure, so essentially a mixture of bainitic ferrite, high carbon enriched austenite, and martensite. We have, in particular, two morphologies of this kind of austenite. In particular, we have filmy retained austenite, very rich in carbon, very stable with temperature, and also from the point of view of mechanical stress application. It's very stable and it tends to transform a very high level of deformation. Then we have also blocks of retained austenite, which are less rich in carbon and so less stable and more prone to transform in martensite. We have to avoid in this kind of steel huge and very large blocks of austenite because they can transform in the very early stage of the deformation, so have a negative effect inside that they give immediately a brittle phase inside the material, and they can deplete the very high and interesting ratio between tensile strength and ductility. This kind of steel are able to reach 2 gigapascal of tensile strength, combining a very high ductility as fracture strain above 15% and around 22%. One of the advantages of this kind of steel, despite of the mechanical properties, are the low cost, because we don't have very expensive alloying element in the microstructure, in the composition, sorry, chromium or nickel, and the production process is very, very simple. And essentially, we don't need complex heat treatment, but just austenitization and isothermal treatment at low temperature, in particular between 400 200 degrees. These are two micrographs of this kind of steel. The one on the left was taken by me on one of the steel that I studied during my first year of PhD. And with this steel, we published those two papers in collaboration between my university and the University of Magnitogorsk. The second micrograph is a TM bright field micrograph from Professor Garcia Mateo from Madrid, and it shows the carbide-free bainite, so consisting in austenite films and retained and ferrite. And as you can see, the dimension of these features in the microstructure is very small, in the order of nanometers. The Y-high silicon steels, high content of silicons allows us to suppress, in some case, but in general, retard the precipitation of cementite, which is a brittle phase, and which can reduce the strength to ductility ratio in this kind of steel. Some words about the Magnitogorsk reaction, which is very, very important. Magnitogorsk reaction is a diffusionless, so it's a displacive transformation of retained austenite into ferrite with a plate shape. And there is a power equilibrium condition during its transformation. And so except for carbon, all the elements in the does not diffuse during the transformation, but carbon, after formation of ferrite, partitions into austenite, enriching austenite and increasing its stability. As the content of carbon of austenite increases, and as its size decreases, the higher is stability of retained austenite. So that's why it's important to control the transformation. Higher is the temperature of the transformation, faster is it the kinetic, but in general, coarser is the microstructure. So it's important to try to reduce as much as possible the temperature at which we obtain bainite, because we can have a finer microstructure. This is the fact that at lower temperature the microstructure is finer is related to the mechanical property of transforming austenite, because at higher temperature it has lower yield strength and can accommodate coarser plates of ferrite. So we have tried to reduce as much as possible our temperature of transformation, considering also the time, because it will be longer, to obtain this nanostructure bainite, which is very, very strong and tough at the same time. Strip steels are commonly used in the automotive industry because they allows us to reduce a lot the weight of the cars, and so we can reduce the oil consumption and the emission of CO2, and because we can reduce a lot of the thickness of the parts and ensuring at the same time very strong structures. One of the other main important field of industry of this kind of steel is the railway industry. For example, Professor Badesha from Cambridge, which is one of the most important research in this field, designed of a triple-assisted carbide-free magnetic steel for the realization of the channels of the railway which connect France and UK. Our steel, essentially me, during my PhD, I'm studying this kind of steel, so it's a medium carbon steel. Normally, a lot of magnetic steel has higher level of carbon, but we have some problem with welding, for example. So we use a lower content of carbon, and we have a very, very high silicon level, about 3%. Normally it's in the range between 1 and 2. And we have 2.7% of manganese. We simulate with some commercial software the critical temperature as a binite start, multi-site start, and also a 1/8 temperature to design the heat treatments. We perform heat treatment consisting in partial or complete austenitization and isothermal treatments in the range between the martensite start and binite start for different times. After partial austenitization treatment, we so in order to have a starting microstructure in half austenite and half ferrite, after 30 minutes of isothermal treatment at 400 degrees, we obtain this microstructure, which is consisting mainly in martensite and ferrite, so not the correct microstructure that we were expecting, with some blocks and huge particles of retained austenite. In this case, the material was very, very strong, but so the tensile strength was around 1.7 gigapascal, but the elongation was very, very small, about 5%. So we moved to complete austenitization treatment and lower isothermal temperature for magnetic transformation. So we start exploring the range between 250 to 400 for different time, from 30-minute treatment to 2 days, so 48 hours, sorry. And we obtain this kind of microstructure, as you can see in the SEM micrographs. So very, very fine magnetic ferrite with film of retained austenite and some blocks of retained austenite and a small fraction of martensite. We arrived to stabilize maximum 16% of austenite in the matrix, and with very high carbon content, around 1.2%, according with the theory and the T0 curves. We observed that increasing the temperature, we have coarser microstructure. So we arrive at 250 degrees to obtain a bainite with dimension the laths around 50 nanometer to 150. And we observe that increasing the isothermal treatment condition, we have a higher content of bainite, unless we can have 100% of bainite because it's an incomplete transformation. But we also increase the amount of retained austenite, but we are able to stabilize, and we reduce the final content of martensite, which is hard and brittle. This is more in detail the microstructure of this kind of steel. As you can see from the TM micrographs and from the field emission micrographs, we have films of retained austenite and magnetic ferrite, very, very small. So we can have a material with very high stability from the point of view of the retained austenite, but which can give us very high strength and ductility. Unfortunately, I didn't have a lot of time and amount of material to study the mechanical properties, but I'm going to do in these next months, also from the point of view of wear test and fatigue. But I did some preliminary tests, and we obtained very, very interesting properties. So 1.7 gigapascals of fracture of tensile strength, yield strength of above 1.4 gigapascal, and elongation above around 22%. And this is a micrograph of the microstructure near the fracture zone. And as you can see, it's possible to observe that there is no presence of blocks of austenite. We have just martensite and some films of retinoids, which remains in the microstructure because they are very, very stable also against transformation. And from the X-ray pattern again, near to the fracture zone, we observe that the big part of the austenite is disappear and transforming in the martensite. For the future work, I plan to explore very, very detailed the mechanical properties, also not only at room temperature, but also high temperature, and to I want to study also the wear properties of the material, because this kind of steel are very promising, as I said before, in the railway application, because they present very, very high wear resistance with respect to standards pyrolytic steels. So for me, it's okay. I finish and I open to your question. So thank you for your kind attention.
Thank you, Mati. Do you hear me?
Yes, yes, of course.
Thank you for your report. So, colleagues, we have time just for one or two questions.
Okay.
Two questions from me.
Yes.
Not questions, but just for discussion. Do you plan to research energy absorption properties of such steel?
You mean impact toughness, or
with different strain rate, with different strain degree, so on and so forth?
Yes, I'm thinking to perform a standard tensile test with a different kind of strain rate, because the strain rate can influence the martensitting transformation. So I want to try low values and higher values of strain rate. And I want to do also interrupter tensile test. So apply different levels of strain to understand how the transformation inside the microstructure happen. So at which degree of the plastic deformation the austenite start transforming into martensite. Yes, of course. This is the future plan.
And also, where did you obtain your samples?
The first experiment were made with the wires that you provide me last year. But now, before Christmas, we bought an ingot of 50 kilograms of the steel. So we contact a company here in Italy, and we ask them to produce us an ingot with the composition that we designed together during the project between our two universities. So now I have huge quantity to work.
Yes. May I ask contacts of your partners for production of such steel?
Yes, sure.
Yes. Okay. Thank you.
Thank you.
We have to go to the next report from Daria Kamkova. You're welcome. Switch on your microphone.
Sorry. So, can you see my screen? Yeah?
Yes, yes. You're welcome.
Good morning, good afternoon, good evening, good night, if you sleep already. My name is Daria, I'm from Institute of Metal Physics in Yekaterinburg. And before I start my presentation, a few words in honor of Professor ZHILYAEV. It's a funny thing, but I met him for the first time in Magnitogorsk that I visited from the first time because there was Magnitogorsk Materials Week for the first time. And this guy, this person, he was so supportive, so kind and so amiable. And I was pretty sure it would be my last visit, but he was so friendly and he was so enthusiastic about young scientists. So it's a great loss that he passed away so soon, because he was a fine gentleman, he was a wonderful person and a top-notch scientist. So, and let's turn to my presentation. Today I'm going to present you my topic, low temperature extrusion and rolling of pure magnesium, devoted to evolution and microstructure and crystallographic texture. Actually, I have already presented a big part of this presentation earlier. But anyway, I think it would be interesting with such tiny things to add. So, it is known magnesium and magnesium alloys are of high interest that last 10 or 20 years as at first slightest structural materials, and also they are on the focus of for medical application. But unfortunately, magnesium ductility, formability, and especially extrudability are poor. For example, here you can see, this is from the article, here I present some authors. They performed ECAP deformation of single magnesium with different initial texture of sample. And as you can see, at each orientation, samples were destroyed. And these experiments were performed at room temperature. Actually, most of experiments with magnesium and magnesium alloys are performed at high temperature. For example, from 100 or 150 degrees, because mostly because room temperature deformation for magnesium is a lower temperature deformation, cold temperature deformation. At last 10 years, we see the high attention of scientists to extruded magnesium alloys. As you can see here, this is from one of this data from one of article, and as you can see here, this is some how to put it, search for magnesium alloy and extruded magnesium alloy. And as you can see, through years, the interest of people, both science and industry, rise for magnesium. So we decided to create a method to deform pure magnesium, mostly at room temperature, and at the same time we wanted to see the influence of the initial texture of magnesium at its deformation behavior. Actually, such kind of experiments were performed in Kalmyshev, if I'm not mistaken, at 90s. And as we created our own method, someone called it as unequal angular channel extrusion, and we called it just lateral extrusion. This method help you to produce thin magnesium plate without some additional treatment. For example, if you want to have some plates from ECAP samples, you have to cut thin samples and then roll it. And in our method, we just take a cylindrical sample. You can see the sizes of these cylindrical billets, put it inside steel container and just apply some pressure, and we received a thin magnesium plate with thickness of 1 millimeter or a bit bigger. Here you can see the initial structure of magnesium billet. It's a coarse grain structure, and also we could see some twinning inside. Is usual thing for magnesium, about 12% in ingot, magnesium ingot could be found. So here you can see the equipment we used. This is our hydraulic press with a force of 10,000 kilonewton, and this is lateral extrusion tool set, which have been designed by our engineers. And this is the end of the experiment. This is magnesium plate. And this is, I will tell later what it is. Anyway, and here you can see the magnesium plate right after the experiment. Unfortunately, I was a bit stupid to divide it into two pieces. But this is the beginner, the initial part of the plate. I mean, the first material that flows at the beginning of deformation, and this is part of plate that flow in a stable state of deformation. And here you can see the good beauty part of this plate, because it's a bit ugly. But this is a good one, and we could roll it. As you can see, there is a lot of cracks on the edges of the plate, and if we provide information further, there is no any cracks, and plate seems to be quite good. Okay. Here you can see the result of X-ray, just a second, X-ray analysis. This is lines before deformation. I mean samples ABC with different preferred orientation of grains. And actually, we decided to make a theoretical estimation of which kind of sleep systems could be activated after lateral extrusion deformation. For that, we just took all plates, all planes, all preferred orientations we could find registered during X-ray analysis, and calculated Schmidt factors. Actually, here it's not the whole table of Schmidt factors. They are just sample examples of high values of Schmidt factors. And we could say that theoretically, the sleep system with such high Schmidt factor could work during deformation. However, based on literature data, we could say that even if, for example, basal system, the commonly used sleep system in magnesium, if this system showed the Schmidt factor about 0.035, it still could be activated because basal system, it's the easiest system and it have the lowest critical resolved shear stresses. In comparison, for example, the pyramidal system or prismatic system. Actually, this is why most of the deformation methods performed at a high temperature, because at high temperature you can turn these systems and to make them work. One of the most asked questions for these experiments or research was about deformation induced heating. Of course, in each deformation method, in each deformation experiment, there is some deformation-induced heating of sample, even if we said that we performed it at room temperature. Of course, we decided to make mathematical estimation of such heating, and based on our calculation, where we have to include the geometry of our equipment tool, the geometry of the sample, the geometry of the cross-section channel, yeah, and we found out that the temperature of magnesium in deformation localization zone could achieve about 75 degrees, but it's only all based on some math. And then we decided to provide an extra experiment to evaluate the temperature during deformation. Unfortunately, we couldn't be able to take the image with, with the distribution of the temperature during the process. So we decided to put a thermocouple. Here you can see the place where we put thermocouple to measure magnesium temperature during deformation at cross section. And here you can see the plot, temperature versus time. And as you can see, the whole process is very fast, and the temperature marks the highest temperature of the magnesium. It's about 140 degrees during the process, I mean, after the beginning. Actually, we think that that's why, as I show you at the end, here you can see that at the beginning of the deformation, magnesium sample is not so warm. There is not so heat. He's not heated as much to flow freely. And during the process, his temperature achieved about 140 degrees. And this is the minimal temperature for magnesium flow. So here you can see some results of texture and magnesium microstructure. Here you can see ABC connected with the initial preferred orientation of the samples. And as you can see, this texture is quite different. Actually, I didn't mention it. Yeah. At the beginning of the process, all samples have different orientation, preferred orientation, yeah? And after the deformation, the main the most grain size grains have orientation, basal orientation. However, we can see that the basal texture is weakened by the different orientations. And you can see it on our texture. It is ZHILYAEV. Actually, also you can notice that there is structure which tells about dynamic crystallization process. It's a typical when we have the model structure with big grain size, big grains surrounded by smaller ones. And I can't say that we achieve nanostructure, and I can't even say that we achieved ultrafine grain structure, but in some areas of the materials, we can register ring circle diffraction, which said about high angle presentation angle. And the grain size depends on the preferred initial orientation. The smallest one in the third sample, where the average grain size is about 102 micrometers. That is quite good result for magnesium. Here you can see some tensile test for these plates, and as you can see, the highest elongation observed for the sample C, and the bigger tensile test for the sample A. The good one thing that we can roll these plates at room temperature, but unfortunately we hope that we could achieve finer structure, but we failed. Actually, during rolling, there is some kind of recrystallization process. That's why, as you can see, there could be fine grains with 40 micrometers. It's presentation degree. Oh, sorry. They could be found grains with 40 presentation degree and 40 micrometers and bigger. And actually, we could roll plate up to 10 micrometers in thickness. But the interesting fact that the size of the grain could be compared with the thickness of the plate. And here's some result of tensile tests. This is comparison of magnesium plate A and mechanical properties for magnesium foil of 150 micrometers. And here you can see the tensile test of 150 micrometer foil at different rates. Of course, there is no superplasticity, but maybe we could perform, we hope to perform in future experiments at lower rate, and also we think about to provide experiments with changing rates during the tensile test, because in this case we can based on obtained result in future, we could say what kind of mechanism could work in such deformation. And here just a couple results of cryogenic rolling. The small summary of that. Here you can see the structure texture of magnesium 1 millimeter plate, and this room temperature rolling, cold temperature rolling, means cryogenic rolling temperature. Yeah, and the main difference between this and this, that actually at room temperature, the main mechanism of deformation is dislocation slipping, and during the cryogenical rolling, it is twinning at the beginning of during the rolling. Actually, it's a common thing for HCP materials. For example, in titanium, scientists observed the same. And also we found work about deformation of magnesium alloy at cryogenic temperature by compression, and they came to the same conclusion that at cryogenic rolling and cryogenic deformation, the main part of deformation is the main mechanism is twinning. So there is a couple of conclusions I could repeat if you want, and this is thank you for your attention, and I'm ready for any questions if you take my point. Okay.
So thank you for your report.
May I ask?
Of course, of course.
Daria, what do you want from rolling? What is your goal to use rolling?
Actually, in Ural Federal University, as I know, it's a long story. So I know they have some kind of, not experiments, but they provide, just a second, I put my thought together. They created membranes. They used very thin aluminum foils, and they used some special chemical treatment to obtain thin membranes for pharmaceutical and for chemical industry. And now we are on our discussion to do the same thing, but with magnesium. But for that, we have to again from the start create some chemical treatment, because it's very special for each material. Also, it could be useful in future. Maybe this method could be useful to obtain thin foils of magnesium alloys. But unfortunately, alloys works only at high temperature.
What level of reduction do you want to get?
How thin you want
it? As high as possible, as less as possible.
As thin as possible.
As high as possible. Yes or no?
Yeah, yeah.
But there is a problem, because you use cryo rolling, and you have big reduction. You have a very rapid increasing of the temperature.
Yeah.
And you can lose.
I do understand this because as sooner you have your sample, the lower the temperature of heating of this sample. And of course, cryogenic, for example, of foils, it's nothing when we start to roll it. I catch it. Maybe up to talking about cryogenic deformation, maybe there is some point to provide deformation up to 100 micrometers in thin. And further, it's...
From what size?
What size?
The absolute reduction.
100, you mean the thin of the foil?
Well,
I don't know.
For the reduction, what is the reduction in percent?
From millimeter to 100, somebody calculated it.
From what thickness?
The sum deformation of such materials is about 6. I mean, true stress is the 2 from lateral extrusion to...
It depends of the quantity of passes. It depends of the could be different reduction on every pass.
Colleagues, excuse me, we have one question from Professor Lies, and we should start lecture
Professor
Cabrera.
I will come once again and we discuss all this, I think.
Yeah. Thank you. Very interesting talk, very interesting discussion as well. So if I understand well, at the high temperature, you switch on the different slip systems, which are not there at room temperature. Mm-hmm. Does the pressure influence the temperature of the where you switch the slip systems?
We don't use any preheating. We don't use any preheating of equipment or materials. It's just under the pressure.
So how much pressure do you give? I missed that maybe.
Okay, thank you. Sorry. It depends on the preferred orientation. For example, just a second. The maximum pressure for deformation of this experiment is about 1.2 gigapascal.
1.2 gigapascal, right?
Yeah. For this sample is about 0.9 and 0.7. It depends on the orientation, because in this case, it
right. And so that's if I understand well, even at lower, say, room temperature, that suppresses some of the twinning? Or you still have the major contribution of twinning?
We found some twinning traces during our transmission electron microscopy, but I can't say that a common thing for our plates. Mostly it's dynamic crystallization structure.
Thank you so much. Very rich and interesting talk. Thank you.
Thank you.
Maybe you will continue your discussion on Magnitogorsk rodent practice. So now we have our guest from Spain and from Mexico. With early morning, I think Jose Maria Cabrera, you're welcome. Nice to see you.
Hello. Can you hear me?
Yes, everything is okay.
Okay, so let's go to share the screen. And I guess that you are, let me see. I think I am having a problem with maximizing the screen.
Yes.
No, something is.
Oh, try to restart the screen sharing.
Sorry. Yeah. Oops, something is wrong. Okay, I think
yes,
that now,
yes.
Now you see my full screen, right?
Yes.
Okay, so thank you very much for your kind invitation to participate in this symposium, in this conference, in memory of my very good friend, Alexander ZHILYAEV. Yes, as you mentioned, I am not really connecting from Spain, and I'm right now in Mexico, but now it's here. We are in the really early morning. But I hope that the connection works okay. So my talk will be related to the welding armco iron after nanostructuring by equal channel angular pressing. But first, I would like to make some words in the memory of Alex. I would like to say that Alex, the Alex connection with Spain was quite large. First, he spent some time in the Autonomous University of Barcelona, and later in CENIM, in the National Research Center of Metallurgy in Madrid, or in materials in general, as he got one of the most important and prestigious awards in Spain, the Ramon y Cajal grants. Then back to Barcelona, Alec was awarded with a Technospring grant from the regional government of Catalonia. So he joined us for 2 years, 2017 and 2018. And after that, he got the mega grant project in Magnitogorsk. His stay in our university was absolutely beneficial and fruitful for our research group, where he was fully integrated. While he was with us, he participates in many lectures concerning severe plastic deformation and attended conferences in Spain, United States, Japan, and also in Mexico. I would like to say that, well, there is no discussion about his magnitude as scientist, that this is out of doubt, but I would like to focus on his personal attitude, his kindness, his affability, his approachability, friendship, and humanity left a very deep mark in our lives. From a personal point of view, I lost a very big friend with whom I shared very nice moments. He helped me to develop as myself as a researcher, but most importantly, as a better human being. Alex will stay forever in my memory. I continuously miss him. I have prepared a small tribute to him using a very popular Catalan song, which is called The Song of Birds, played by Pau Casals, using some of the images that I have from him during these 2 years staying in our department. This presentation takes around 2 minutes, and I hope you can follow the sounds. I will put the sounds at maximum. So let's see if you can listen to that. And when this music tribute finish, I will start my presentation.
Дима.
Professor Cabrera, we don't hear your sound. You can restart your share screen and put in the left bottom place share sound, something in English.
Okay, I will pass you the presentation with the sound, and then now we will only see the pictures.
Yes, yes.
It's only 2 minutes.
Нет, нет, это... Ой. Okay, so thank you for your attention, and then I will move now to the topic of my presentation today. This is a cooperative work with some colleagues from Mexico, Professor Ignacio Mejias, and from Argentina and Russia, Professor Jairo Muñoz. He spent some time in the Mises University. Now he's back in Argentina. Part of most of these results were also obtained in our university. Well, as you may know, the science and technology of materials undergoing severe plastic deformation has evolved enormously during the last years. Good part of this knowledge was presented for the very first time in an international workshop held in Moscow in 1999. And since then, the contributions, or most of the contributions in this area are coming from Russian researchers, where they have had significant contribution. Although strictly speaking, the severe plastic deformation phenomena in modern time was pioneered by Professor Bridgman at Harvard University, when he was studying the sort of high pressure torsion applied to any kinds of materials. However, as you may know, the severe plastic deformation is very well known since ancient times, because the basis of the famous Beiliang steels of China, or the Boots steels of India, or the Damascus steels in the Middle East are based basically on severe plastic deformation. But in modern times, we have to go to the last century, in the 30s. Although most recently results are obtained since the almost the end of the last century. It's interesting to see that in 2003, Professor Terry Lowe and Yuntian Su made a very interesting review concerning the commercialization of nanostructured metals by SPD, and they observed that at those times, the number of papers published were around 1,000. Interesting number of patents were already available at those times. They were detecting the potential market for application of this process. So in 2003, they conclude that the SPD technology was emerging. There was a market that was waiting for products obtained by SPD. Well, the same authors, 14 years later, made a review again about the scientific and technological foundations for scaling production of nanostructured materials, and they realized that the academic and basic research have grown enormously, but surprisingly, the industrial application and the industrial scaling had not progressed in the same direction. Well, if we analyze the situation, the real situation nowadays, we see that the SPD methods are basically located in a tier level of 3, 4. So we are not able to jump to the industry yet, at least in a very massive way, just very small or few cases. We are producing materials that are nanostructured, and then they are fully used for the industry. But most of the research is still done
in the academy, in the universities, and we are not getting the jump to the industry yet. Well, these figures may seem disheartening because after so many years researching, we don't find a way to pass this to the industry. And then we should think about why this is happening. The reasons regarding to this fact can be found in that we have to face some improvements regarding what we have in the laboratory. First, we need to provide continuous processing instead of this batch processing that we have most of the processes that you can find in the academy. Second, we have to increase the size of the samples to be processed. Otherwise, we will not be able to use them as bulk materials. Then we have to focus also on developing flat products. The last presentation was a clear example of that, how to develop flat products with large severe plastic deformation. And fourth, and according to me, very important, is to focus on hybridization of properties. And this is, according to me, a key point. So we should ask ourselves if it makes sense to increase the mechanical properties by SPD. If we think in SPD just as a way to increase the mechanical properties, we will most probably fail and we will not be able to market our solution. Of course, the original idea behind SPD was to develop a very fine nanostructure in order to improve the superplastic ability of the material. But many people immediately realized that the mechanical properties were also multiplied by a factor of 5, 6, 7, because this refinement of the microstructure. But if we think in SPD processing just as a way to increase mechanical properties, we will be probably failed when marketing this solution because this is not a cheap solution. It's much cheaper to alloy the metal, and then we will increase the mechanical properties at the same level. But if we think by functionalizing the materials in hybridized properties, that means if we increase the mechanical properties in terms of strength, and at the same time we do not penalize a second property, second functional property, then this can be a perfect solution. The use of SPD processing to obtain nanostructure materials. For example, and many authors have been working on that, increase the strength in pure copper. This can be done by SPD while keeping high electrical conductivity. Most of the studies indicate that the electrical conductivity is almost not penalized after SPD. So this can be perfectly an industrial solution. The only problem is to scale up the size of the component that we manufacture. Another solution that I think this is really being used nowadays is to increase the strength in pure titanium while keeping high biocompatibility. You know that sometimes we use alloy titanium because we increase the mechanical properties, but then we are penalizing somehow the biocompatibility. So if we are able to increase the mechanical properties without penalizing biocompatibility, then this can be, again, another good solution that have potential to be transferred to the market. And a third option is the one I am going to work here. The one I am going to present here is to strengthen the mechanical properties in pure iron or very low carbon steels while keeping weldability. You know that if you increase the mechanical properties of steels by alloying, you are penalizing weldability. So this cannot be sometimes a good solution because, for instance, the automotive industry is demanding steels of high mechanical properties, but at the same time, they should be weldable. So one way to increase the mechanical properties without affecting the weldability would be to apply severe plastic deformation to pure iron or a very low carbon steel. So this is what I want to show you. This is a summary of some of the research we have been done in our research group in the last 4 years. These results are already collected in this manuscripts that you can see listed in this slide. And the final objective here is to fabricate a nanostructured AMCO iron by using equal channel angular pressing. Then verification of the microstructure and the mechanical properties that we are obtaining, and then check the weldability by the gas tungsten arc welding, also known as TIC process. So these are the 3 main topics that we wanted to check. So these are the experimental details of our work. First, we selected an Arcom iron, which is basically a pure iron with very low carbon, silicon, and manganese content. So basically, it's pure iron. The material was supplied in draw rods, and then we annealed these rods, and the final grain size was around of 19 micrometers. Then we cut these rods in bars of 8 millimeters in diameter and 100 millimeters in length. And then we use our ECAP facilities, which is based on an 80 tons press with dies of 90 degrees following the BC route. And then we ECAP the material after 16 passes using molybdenum disulfide as lubricant. Then from these samples, we will extract by machining mini tensile samples with the dimensions indicated in this slide. So really small one, directly machined from the rod bars. And then we perform the tensile test to characterize the mechanical properties, the static mechanical properties. But not also that, but we also analyze the fatigue behavior of these materials. Remember that in many applications, the component must be designed according to the fatigue response, not to the static response. In this case, we limited the study to samples after 8 passes. And as well, we did some fracture toughness analysis, because you know that this sort of materials are accused or are signed as brittle materials because they have relatively limited ductility, and some authors appoint that as a brittle behavior, and we will see later that when we analyze the fracture surface, we don't see brittleness at all. And indeed, we measure the fracture toughness, the K1C value of the samples after 8 passes, and you will see that we are absolutely obtaining a tough material. And finally, we did welding test for our samples from our rods at 8 passes. We cut the rods by the half, and then we put them again together, and then we use the tungsten inner gas technique, the gas tungsten arc welding without filler material. So we only just put together the samples, and then we prepare boot joints using this tungsten electrode around the samples using 3 welding conditions. In these welding conditions, we only change current intensity and voltage. So in other words, we change the heat input into the system. I will summarize the results. I will not give very large amount of details about the experimental preparation, about the experimental measurement, the experimental characterization, but you can imagine they are quite conventional. So first we analyze the microstructure using EBSD, and then we can see that the material, this is the material in the as received condition, this is in the as annealed condition, and then we see the microstructure after 1 pass, 2 passes, 3 passes, 4 passes, 6, 7 passes, finally 8 passes, and 16 passes. You see that the scale is changing in every step, so that means that the material is starting to get reduced in terms of grain size. Indeed, we analyze the distribution of low angle grain boundaries and high angle grain boundaries, and we notice what is expected, that at the very beginning, the amount of low angle grain boundaries increases in the very first steps of ECAP passes, and then starts to reduce and get a sort of a steady state with the number of passes. So around of 8 passes, the material starts to get stabilized. So the opposite happened with the high angle grain boundary. So at the very beginning, we have a large amount of high angle grain boundaries. Then this decreases very much, and then it starts to increase. And then this is the reason why at the end we start to have a real recrystallize between new material. Well, we measure this grain size using very different techniques, since X-ray diffraction, transmission electron microscopy, transmission electron microscopy coupled with EBSD, EBSD in scanning electron microscopy, considering and without considering subgrains. And in all of them, we observe exactly the same result. There was a heavy grain size reduction. And then after 8 passes, more or less, the material gets stabilization. Or at least we can say that from 8 passes to 16 passes, the reduction is so minor that in practical terms, there is no many sense. So keep here the figures that we get at 8 passes. So we are going to have a grain size of around 275 nanometers measured using EBSD in a scanning electron microscope, considering subgrains. Of course, this can change a little bit depending on the techniques that we are using for characterizing the grain size. In terms of mechanical properties, what we got is that the material in the anneal condition was displaying a yield stress of around 200 megapascals, but this yield stress increases very much after the number of ECAP passes. And at 8 ECAP passes, these 200 megapascals were around 800 megapascals. Okay, so even if we go to 16 passes, we are approaching to 900 megapascals. That means that we are getting mechanical properties very similar to that offered by medium carbon microalloy steels or the modern advanced high strength steels that the automotive industry is using, such as triple steels, complex phase steels, dual phase steels. So that means relatively highly alloy steels, while in this case, the big difference is that our material is basically pure iron. Of course, you immediately notice that the total elongation is not so large, it's around 20%, and most of this elongation is heterogeneous. So the material shows immediately necking, and the total strength is basically concentrated in the necking area. Okay, so this is the magnification in the elastic region, or the moment in which you get necking, and you immediately see that the homogeneous deformation is relatively low, but the total strength is quite large. If we check the microstructure in the scanning electron microscope, we observe that we are having a almost fully ductile microstructure. So we cannot consider that even the necking phenomena occurs very fast. We cannot think that this material is brittle. The material is fully ductile. The results that we get using by the fatigue analysis, and this is the typical SN plot, and then we observe that the material in the as received condition, anneal condition, is displaying this fatigue curve, while the material after 8 passes is increasing a factor, well, a relatively large factor, more than a factor of 2 or 3, the fatigue limit of the material. Even at relatively low cycle regime, we get very good, very good risk. Well, no, this is not exactly low fatigue regime. This is the static tensile test. So in low cycles fatigue, we don't have results. Sorry, but in the high cycle fatigue, the behavior was quite better than the material in the annealed condition. So that's our good news also. Regarding the fracture mechanics, the fracture toughness, the study was not very large, but we were able to obtain in the sample processed after 8 passes fracture toughness K1C around 42 megapascals square meter. And that is a relatively significant value that is indicating clearly that the material is having a tough behavior. Of course, one have to think that this is the behavior we need in service. So the material in service will have a very nice behavior, with very tough behavior, although we will not be able to continue deforming the material because the total strain that the material can accept is relatively limited. But if we are able to obtain this material, the final shape of the material after the ECAP process, then when we put the material in service, the mechanical behavior will be very good one. We will have a very good mechanical properties, tensile stresses, we will have a much more higher fatigue behavior, and then we are having fracture toughness really large. Regarding the welding results, our main concern was if we were going to lose the microstructure. Of course, we are going to heat up the material, and then most probably we are going to face with some grain growth. But because the chemical composition, we should not be expecting undesirable microstructures such as martensites and so on. So the main concern here is to check how large was the ferritic grain that we were obtaining after the welding processes. These are the optical images that we have in our boots. The one on the right and on the left-hand side correspond to the lower heat input. The one on the right-hand side correspond to the higher heat input. And what we observe in all 3 cases is that we have 3 different zones. We have a fusion zone, of course, where the material melted. Then we have what we call a heat-affected zone, heat-affected zone 1. We will see here immediately that we are facing here a very large grain growth. And then we have what we call a heat-affected zone 2, an area where we don't have anymore the small grain sizes of 275 nanometers, but the grain size is still quite fine. This is observed clearly in this optical reconstruction of our material. These are the 3 weldings that we did it. So these are the 2 halves that we put together. Of course, the welding without adding filler is only done onto the surface. And then we can see here what happens when we increase the heat input. This is the length of the fusion zone that is quite constant, a little bit larger in the condition with the larger heat input. Then this is the heat affected zone 1, which is moving to larger values as we increase the heat input condition. You can immediately notice that we are having larger grain sizes here, and in the center we have the so-called heat affected zone 2. It's a zone that also is getting reduced when we are increasing the heat input values, but in this area we are keeping a relatively fine grain size. Of course, it's not the grain size that we got during the ECAP processing, but this is still quite fine. Indeed, the results are summarized here. We have the evolution of the grain size across this section. You notice here that we are facing relatively good, relatively fine grain sizes in this fusion zone, although the important thing is that we are obtaining a secular ferrite in this fusion zone. In the heat affected zone 1, the grain size was larger, as already mentioned. You see here also the grain size is larger, but curiously the hardness values were higher than in the central zone. In the heat affected zone 2, the grain size is smaller, but the hardness is not so large. Summarizing, the larger heat input promoted larger heat affected zone 1 and shorter heat affected zone 2. This is identified in these images by the color. So the blue color is indicating the length of the heat affected zone 2, and the white color the length of the heat affected zone 2. We also observed that the larger hardness in the heat affected zone 1, although providing larger grain size, is associated to larger internal stresses. This is the reason. This has been also reported in the literature, that you can have larger grain sizes, but because you are in the vicinity of the fusion zone and then you have high cooling rates in this area, then you get a lot of internal stresses within your material, which are promoting that the hardness values in this area are relatively large, besides the fact that you have a larger grain size. In order to verify with much more detail, because we were not able to measure the heating rates in our welded samples, we decided to perform 2 control experiments in our quenching dilatometer. And we did this test under 2 conditions. We heat up very fast at heating rates of around 3,000, 4,100 Celsius per second, up to 950 and 1150 Celsius degrees. And then we hold for 2 seconds, almost 2 seconds, and then we immediately quench our materials and our samples. So the real behavior should be a lower cooling rate, but what we wanted to do with this experiment was to check the potential of the process to see what is the microstructure that we would be getting under control experiments after high heating rates and high cooling rates. And these are the results in terms of the microstructure. When we heat up at 950, the microstructure is fully ferritic, quite equiaxic, while when the heating was carried out at 1150 Celsius, the final microstructure was finer and acicular, was acicular ferrite. In terms of the microstructure, the grain size evolution in the is compared here. This is the microstructure of the sample after ECAP, after 8 ECAP passes. This is the original, the initial microstructure, and this would be the this is the microstructure of the materials after doing the dilatometer test. You see that we are still capturing, especially at 1150, we are still capturing or getting some nanostructure or ultra-fine microstructure within the material. Regarding the amount of dislocations, of course, we notice that we are in the middle. We are not, of course, with the, we don't have the same level of dislocations that we have after ECAP process, but we have much more than the material in the anneal condition. And indeed, we are entering in the sample that we have, where we have been simulating the welding behavior, we are still retaining fine microstructure and a large amount of dislocations within our material that is indicating that we are going to retain partially the good benefits of severe plastic deformation. So these results, the total results demonstrate that there is a formation of decreasing low angle grain boundaries fraction and dislocation gradient from the outside to the inside of the bar in the radial direction. And this behavior together with the possible higher residual stresses in the vicinity of the heat affected zone 1 helps to explain the higher hardness values in this area regarding to the zone 2. During the welding processes, the ultra fine grain of the ARMCO iron still retains some mechanical properties and some microstructural features that are typical of the material after severe plastic deformation. Of course, we don't have retained the full potential because the process that we have been using is a process with high heat input, but the dilatometric study suggests that we have still a large potential to retain this microstructure using lower heat input processes. And this should be the focus of the next and future research in this area. The conclusion would be that the ECAP process generated, of course, an ultra-fine grain size material, that the welding conditions generate 3 different zones with different grain size and morphologies. In the fusion zone, we are obtaining a circular ferrite. In the heat-affected zone, we have 2 behaviors, one area with very large grain sizes, but surprisingly with relatively larger hardness values than the other heat-affected zone. The mechanical properties, of course, were reduced compared to the material with 8 ECAP passes, but still they maintain better properties than the initial annealed material due to the promotion of a relatively fine recrystallized grains in the heat-affected zone 2, and the presence of internal stresses in the heat-affected zone 1 and the acicular ferrite associated to the fusion zone. So the dilatometric study suggests that if we are able to use an alternative and modern welding processes using lower heat inputs, we should be able to retain as much as to retain the microstructure, if not at ultra fine regime, but at least in relatively low values. And this would indicate that we are going to have a weldable material with interesting mechanical, still interesting mechanical properties in the welding area. And with this, I finish my presentation. I thank you very much for your kind attention. I am open for discussion if you have any doubt or questions.
Thank you, Professor Cabrera, for your report. I see sun in your window. It was difficult to combine all time zones, but thank you for your presentation. So, colleagues, do you have any questions?
Can I ask a question?
Yes, of course.
Professor Cabrera, thank you for your great report. It was very interesting. At the beginning, you said that there is some difficulties with to apply to use such treatment or for industry. Whether you consider ECAP conform to deform ARMCO iron, for example.
Yeah, that's indeed one of the, we have applied this conform machine in our group, and to this, let me go to check which one. Yeah, here for this application, for increase the strength in pure copper while keeping high electrical conductivity. This is, according to me, one of the solutions. This can be one of the solutions to use the conform equipment in order to get continuous material, continuous bulk material. But there is one problem that has to be solved, but I think it's not so important, but it's more an engineering problem than a real material science problem. The problem of working in a continuous way is that you are promoting a lot of heat. This is not happening in the lab when you are doing batch processing, when you only cap one sample. So the heat generated is immediately extracted by the dyes. But in a continuous system, in a conform system, you need to extract continuously and very fast the heat that you are generated. Otherwise, you are not going to do ECAP at cold conditions, but at high conditions. And therefore, the grain size will not be very fine. But this is just designing of the cooling system, the refrigeration system into your process, and fitting and tuning the ECAP rate that you can accept in your process.
Okay, thank you.
Yeah.
So, colleagues, more questions?
May I?
Yes, yes.
Professor Cabrera, Sergey Zhipsov. I just wonder if you check the thermostability of ultrafine grain condition, just to understand which welding technique can be used to survive that condition.
Yeah, you are absolutely right. Indeed, we have done these studies. These are collected in one of our papers where we analyze the stability of the material. And yeah, we can connect this stability with the welding process that we need. But summarizing, the welding process that we need is a welding process that introduces low heat input. This heat input can be highly focused, can be laser, but what we don't want is that this heat input enters within the interior part of the material, in the inner part of the material. If we are able to do that, we will keep relatively low grain sizes. And what happens in the area that we are going to melt the material is, in the case of very low carbon steels or AMCO iron, is that we are going to get a circular ferrite, which is not so harmful as martensite, and we can accept that microstructure for our material. But for sure, the thermal stability of our materials after ECAP are reflected in the fact that the recrystallization temperature is reduced very much, and this indicated that the grain size, the grain growth happens very fast, and this is why here we are getting grain growth even in the center of our samples.
Thank you.
Yeah.
Colleagues, any questions? So, Professor Pesik.
I have no questions, but I want to tell Jose Cabrera, Professor Cabrera, that in 1 or 2 days I will connect with you because I have interesting information.
Okay, thank you.
Okay, thank you.
And also congratulations for the organization of this 3 days conference in the memory of our well-beloved Alex ZHILYAEV.
Thank you for participation, and of course.
So, colleagues, it was the last report, but important report today. I have a short presentation in non-scientific part. One moment. This is some kind of announcement. Do you see my presentation?
Yes.
So today we want to announce the 6th International Young Scientific and Technical Conference. This is a very fresh release because we made this this decision, this conclusion today. because we saw the feedback from our colleagues, feedback during all these 3 days. Just a few words about the conference. So, as you know, we're located in beautiful city Magnitogorsk, near the Moscow, and the biggest part of participants knows about it. But anyway, the main audience of our conference is young researchers in the field of materials processing, in general, metal forming. And we every year we try to make this conference better, and we try to apply some features which can be interesting for young researchers. First of all, participation in our conference is free of charge. In our conference we have best presentation competition with some advantages. For example, we provide free accommodation and Scopus indexed publications for the best researchers. And during our conference, we have usually 3 sections. Because the main idea of our event is Magnitogorsk is place where theory and practice meet. Because we are located not only on geographic point of meeting between Asia and Europe. Also, we want to attract theoretical and practice and fully practice-oriented research in one place, in one event. Every year we provide a unique industrial tour to the biggest industrial metallurgical plant in Russia. And we try to combine different divisions of our metallurgical plant. Because only in this place you can see the full cycle of industrial metallurgy, from ore to bolts, screws, wire, and so on and so forth. Here you can see our journal partners. This is rather popular journals in this field. For example, our information partner CIS Iron and Steel Review. This is first quarterly Scopus journal. It depends on time when we will organize this conference. We will provide special social events, because we every period of the year we have a lot of sightseeing and attractive places in our district. And the main news today is that conference will, I hope, will occur in first week of December, from 30 of November, on the border between November and December. We have our website. We will modify this slide, this site. But anyway, if you have young colleagues, if you want to be a keynote speaker, if you have your PhD students, you're welcome. And for any information, you can write email to this address, and we will help you. So I think we should we should finish this event, and I provide the speech right to Professor Korchunov to some last words.
Okay, dear colleagues, do you hear me?
Yes, yes.
It's a great pleasure to hear and to see you. It was a very long and intensive scientific marathon dedicated to the memory of Professor Alexander Petrovich ZHILYAEV. And one more time, on behalf of North of Magnitogorsk State Technical University Administration, we would like to greatly thank all of participants for the contribution to the aim of the conference Magnitogorsk Materials Week. Despite of the difference in time zones, the conference program was almost fully implemented. We've lost only maybe 1 or 2 participants. It was not so easy to combine difference in time zones. Nevertheless, it's very pleasant that the conference had a wide geography. We have listened about maybe 50 scientific reports. I would like to thank our respected members of program committee. We also encourage the team of organizing committee, Professor Raab, Professor Pesin, Piotr ZHILYAEV, Ekaterina Medvedeva. Many thanks to Olga Velichka and Kirill Savedyev for development of brand book and website of the conference. Our gratitude to our university financial department and ZHILYAEV Laboratory of Mechanics of Gradient Nanomaterials for financial support of the conference, Scientific Journal Materials Letter for information support. Our special thanks to Dmitry Konstantinov for management of our scientific event, professional management. Thank you very much. Altogether, we've done our best to provide a high level of conference deserving the memory of Professor Alexander ZHILYAEV. We wish you good health and a lot of scientific success. And we are looking forward to see you near future in Magnitogorsk at our next scientific conferences. Thank you so much for participation.
May I have one more?
Да, да.
Okay. The next Magnitogorsk Material Week will be in the autumn, in the last week of October, but it will be in another format. It will be in format for participants. We will invite two or three famous scientists, and they make lectures for a whole week, and all participants who could take part in this conference, in this seminar. But I have an idea, we have an idea, our program committee, to continue this conference. Maybe one time in 3 years, we can organize conferences in maybe name it ZHILYAEV conference. Maybe if you not be against it, maybe I have this idea. And next in 2024, we will organize the conference, the same conference.
So, colleagues, do you want to add something? We have some kind of open microphone if you want. So a few words from me. It was difficult, but it was important. And first of all, I want to say thank you to my invisible team, Кирилл Савельев, Оля Величко, Екатерина Медведева. It was impossible without their support. Professor ZHILYAEV united around him a huge people community with different views, with different ages and nationalities. And while this collaboration exists, some part of his is with us. And thank you very much for spending your time in memory of this wonderful scientist, colleague, and friend. Good luck, and please take care of yourself and your relatives. Thank you. So I think we should say goodbye, but I hope see you soon.
Irene, please, we don't hear you. Please switch on your microphone.
Sorry. Bye-bye from Italy. Thank you very much for the invitation, for the opportunity, for the good conference, and for the good cooperation that we are going to do. See you the next, maybe in, I hope, in Magnitogorsk.
I will answer you. Today I have no time, and tomorrow I will answer you.
Yes. Tomorrow.
And may I say thank you all for the participation in the conference Memory Oleg ZHILYAEV. Invite to scientific cooperation. Thank you.
Okay, we are very okay. That's all. We are very glad to see you next time in our conference, and we are waiting. We are ready to